Hey everybody, welcome back to the channel. In this video I will share everything that you need to know for the MCAT physics and math sections. I personally use these Milesdown Review Sheets to get 100 percentile on the MCAT when I took it a couple of years ago. I'm now a third-year med student, and this was one of the main sources of my content review throughout my studying. I'm going to supplement this review with pictures from Google Images and my own questions to make sure that you're understanding and following along. I hope you find this helpful, and let's get started. So first thing we want to review is vectors and scalars. So this first page is kind of things that you want to know down cold because they're pretty important for the MCAT and also very fundamental things you need to know for the physics section. So vectors it's important to know the difference between vectors and scalars. Vectors are things that have both magnitude and direction, and scalars are just things that are quantities but not necessarily, or don't have a direction. And so the most important distinction here is the one between velocity and speed. That's going to be tested in one way or the other, but basically you want to know that something like velocity or acceleration or force, these are all numbers that are attached to directions. So I can't just tell you that the person's velocity was 5 miles per hour. I have to tell you that this person's velocity was 5 miles per hour going in the west direction. If I just tell you that it's 5 miles per hour, then that's just their speed. And so it's important to know that displacement, velocity, acceleration, and force are all vectors, and speed or coefficients of friction, anything that's kind of a number, is always going to be a scalar. So vector addition is pretty important. They're not necessarily going to ask you to add up vectors, but it is kind of important to understand how it happens. And so what happens is that you take these vectors, so let's say the vector A and the vector B in this image, and let's see, so this is A and this is B, and whenever you add up vectors, you have to add up the point of one with the tail of the other. And so when I say A plus B, then it's important to know that, okay, we start with A is pointing this direction, and then we put the tail of B, and then that gets added up. And so the final vector is one that goes from the tail of A to the point of B, so A to B. It's also important to know that when you're doing vector addition, you can reverse this and you'll still get the same answer. So if you start with B and then you add A to that, right? B plus A is going to be the same vector as A plus B. So that's kind of how you do vector addition. Now, how do you do vector subtraction? Vector subtraction is kind of the same thing. Basically, when you're doing vector subtraction, you want to reverse the ones that's being subtracted, and then you can add them. So let's look at another example. Subtraction. Okay, so let's say A minus B, right? A minus B is going to be, you take the one that's A, and then you're doing minus B, so you have to reverse B. So I'm going to take the vector of B, so I'm just going to draw it over here. So this is A, right? And then B, if we're going to do negative B, then it would actually look this way. So this is the negative B vector, right? So you add A and you add negative B and you get A, and then I'm going to add the tail of negative B. And if you remember, negative B points this way, so it's going to be A and then negative B, and we're adding those two, and we get this vector, which is the vector that goes this way. So that's one way to do it. Now it is kind of important to know that this is not the same thing as B minus A, because B minus A would be this plus this. And so B minus A would actually be going in the opposite direction as A minus B. Okay, I hope that makes sense. Let's move on. So vector multiplication, there's actually two important concepts here. One is you do the dot product, and the other one is you do the cross product. The important distinction here is that a dot product is you get a scalar quantity, and a cross product you get the vector as a result. So a dot product is the magnitude of A times the magnitude of B times cosine of theta. And you have to remember that theta is the angle that A and B form. A cross product is the magnitude of A times the magnitude of B times the sine of the angle, but then you have to remember that this results in a new vector. And this is always something that's confused so many people, me included, which is that you have to find the new vector based on this thing called the right-hand rule. So let's start with the dot product real quick, and then I'll go over the cross product. So the dot product vectors is like this. So a dot product, you would take the magnitude of A. So the magnitude of A is, you find what is what is the, here, let's find a equation for the magnitude. Okay, so to find the magnitude of a vector, you essentially take the x and then you take the y of that vector and you square the two and you add them and you take the square root of that. So it's like the Pythagorean theorem. So you take the magnitude of a vector, so in this case you would take magnitude of A and then you multiply it by the magnitude of B, and then you would take the theta that those two vectors form. And so it's important to know that when you're making the angle between those two vectors, this is also something that confuses people, is you want to take the tails of the two vectors and take that angle in between the two tails. And so that's going to give you the dot product between two vectors. Now let's do the cross product, which is a little bit more complicated just because you have to know the right-hand rule for this one. So this is a good example. So let's take A and B. So A is going this way and B is going this way. Now what I do is, there's two ways to do this. I like to take my full hand, but some people like to do the 3 fingers. And essentially you point your hand in the direction of the first vector, in the direction of A. So you do the same thing essentially as what you were doing for the dot product. So you do magnitude of A times magnitude of B times the sine of the theta, and dot product was cosine of theta. But here you're first figuring out that scalar component, and now you're figuring out which direction does the vector point in for cross product. So you point your hand in the direction of A, and then you curl your hand towards the direction of B. So in this example, I'm not sure if you're going to be able to see it. Let's increase my screen. So in this example, if my A vector is going this way, and then I'm curling my hand inside for the B vector, as you could see in that example, then my thumb is pointing up. And that's kind of how you figure out the direction in which your cross product is going in. All right. So in this example, again, you can see, let's see if I can show you by drawing over it. So this is the direction, this is the direction of A, and then we curl our hand this way to get the direction of B. So now our hand should have curled this way. And then our thumb is telling us which direction the cross product vector is pointing in. So that's how you do that. Let's do another example just so that you have that down. Product vector direction. So let's do this. So this is how you do the right-hand rule, which is, let's say A is pointing in that direction, in this direction, and B is pointing in this direction. So we curl our hand just like this guy is doing this way, and the way that our thumb is pointing is up. So the cross product vector is going to point up. And now you can see in this example A, and then the B vector is this. So the only way that you can curl your finger is by pointing downward to curl that way, because you can't point your finger upward for that. So now you know that the cross product of A and the cross product of B is going downward. Again, it is important to know that the A and B vector cross product, that is not the same vector as B cross product A. And they might try to trip you up on this. I've seen some practice exams where they try to trick you up on that, but it's important to know that those are actually the opposite vectors, because A cross product with B will be pointing upward in this example, and a B cross product with A would be pointing downward. It would be the same scalar quantity, but it would be pointing downward. So that's kind of an important concept to know. All right, so we finished vectors and scalars. Now is the mechanical equilibrium. And this is free body diagrams is kind of the things that you do in physics class in high school or college, where you see like there's this box that's rolling downwards, and your physics teacher is asking you to figure out all the forces that are acting on it. So usually it's going to be this box, and then you'll have like the force of gravity pointing down, and you'll have friction that's going in the opposite direction as the movement, and then you'll have some normal force, which is kind of the contact force in between those two objects. And so a free body diagram is the representation of all the forces that are acting on some object. Now, translational equilibrium is when this object has no net forces acting on it. So a net force is basically when you add up all those forces using vector addition, then you get the net force. And so there's no net forces acting on an object. Now, this is an important point where they'll try to trip you up, which is if there's no net forces on an object, does that mean that that object is not moving? I'll give you a second. So the answer to that is not necessarily, because no net forces on an object means there's no acceleration on that object, as we'll learn when we get the second law of Newton. But an object can be going at the same speed with zero acceleration. Like it can be going at 5 miles per hour without stopping or without accelerating, and that would have no net forces acting on it. It could also be going at 0 miles per hour and just consistently just stay stationary, and that would also have no net forces on it. Okay, rotational equilibrium, so you can imagine like a bowling ball, and normally a bowling ball is rotating, and there's like somebody who's applying a net torque to that, who's applying a force to that, and that's causing a torque, which causing this bowling ball to rotate. But if this bowling ball has no net torque on it, then that means that essentially there's no it's not rolling any faster or slower than usual. It's just kind of either rolling in a constant way, or it's just not rolling at all. And so that would be rotational equilibrium. And then it's important to know that the center of mass is the most commonly used pivot point for something that has rotational equilibrium. All right, displacement and velocity. Now it's important to know, and we kind of already talked about this, which is that displacement is the change in position, and it's path independent. Distance is that scalar quantity which reflects the path traveled, and velocity represents the change in the displacement with respect to time. So it's kind of important to know the differences between all of these. And so let's say that I walk from my house to your house, and then I walk back to my house, right? My displacement is 0 because I haven't actually, throughout that entire time, I ended up at the same spot. My speed, or my distance is actually that plus that. So it's whatever my walk is to you times 2. So that's the distance, and my displacement is 0 because I haven't moved at all. So my velocity here would be 0. My speed would be whatever the distance is divided by the total amount of time. So that's kind of the difference between displacement and distance. Velocity is the change in displacement with respect to time. So it's important to know kind of the difference between that. Instantaneous velocity is the change in displacement over time as the time approaches 0. And this is kind of where you get into a little bit of calculus, which is that if I'm like, let's say my, I'm trying to think of the best. Let's say I'm running a marathon, and at certain points in the marathon, I'm running at like 5 miles per hour, and then 4 miles per hour, and then 3 miles per hour, and then 7 miles per hour. So like the instantaneous velocity is the velocity that I'm moving at this exact point in time. And then the instantaneous speed is the magnitude of that velocity vector. And so the change in displacement again versus the change in distance. All right. Now it's force and acceleration, and this is absolutely fundamental for the MCAT. So the force is any push or pull on an object that results in acceleration. So my dad has this story that he tells me, which is that his physics teacher once asked him to push a wall for 5 minutes, and then he asked them, did you do any force? And the answer is actually no, because it didn't result in any acceleration on that wall. And so a push or pull that results in acceleration. Okay, gravity is the attractive force between two objects. So most people think gravity is just the downward force on something. But the reason why that is a downward force is because essentially this is you, and this is you standing on the earth. And so the earth is putting a force on you, right? This is the earth. This is the gravitational force towards the earth, and this is your force towards the you are attracting the earth, and the earth is attracting you. It's just that the earth has so much more mass that results in a gravitational force pulling you down. But you're technically also pulling the earth up a little bit. It's just you're so tiny compared to the earth that the gravitational attractive force between you and the earth is so tiny in comparison. So friction is the force that opposes motion as a function of electrostatic interactions at the surfaces between two objects. And so there's static friction, which is when an object is not moving, and kinetic friction, which is when an object is moving. And that's equal to the normal force times a coefficient. And this coefficient is dependent on what surface you're looking at. And so ice has a different kinetic friction or static friction as compared to like the chalkboard, and so it's important. You don't need to know like different coefficients, but you do need to know that the normal force times that coefficient is equal to that friction. It's also important to know that this coefficient is going to be different based on static or kinetic friction. So you need to know whether the object is sliding or whether it's stationary to figure out what that force is. All right. At this point, it's probably important to know what normal force is. So I did mention it before, but a normal force is essentially the contact between two objects. And so let's say this is a slide and this is a box. The normal force is going in this direction because it's the contact force between those. So if I'm drawing the normal force on this box that this ramp exerts on this box, it would be going this way. And then it would also have a gravitational force pointing this way. So this is the normal force. All right. A measure of inertia on an object is the mass. And so I remember in 3rd grade, we would learn about masses versus weight, and I would have no idea what either of that meant. Mass is essentially how much stuff is in a material. And it's inertia is kind of like how hard it is to move. And so mass doesn't change based on the gravitational force. It's just kind of like how much stuff is in it. Weight does change based on the force that's being placed on it. And so how we measure weight is usually the gravitational attraction that thing has to the earth. And so weight is definitely dependent on mass. So like if you have more mass, then you have more weight. But the idea is that if you go to a different planet and the gravitational attraction is a different constant, then the weight is going to change, but the mass stays the same because the mass is only dependent on the inertia of the object, which is essentially how much stuff is in that object. All right, acceleration is the vector that represents the change in velocity over time. And so if you were wondering why was I talking about this thing instantaneous velocity before, it's because we use that calculation of what the instantaneous velocity is, and we figure out like how is that instantaneous velocity changing over time, and that's what the acceleration is. And then there's torque. Torque is, I know I mentioned it over here in rotational equilibrium, but torque is basically a twisting force that causes rotation. And so if I was going to draw, let's say this is a bowling ball, right? Or this is just any ball. So if I apply a force that's right up here, then that's going to cause this ball to roll. But if I applied a force like this to the ball at this point, that ball is not going to roll. It won't roll because I'm not applying a force that causes twisting or causes torque. And so important to know, this is always confusing people, but what are these two things? So the first coefficient is the distance from the center of mass that you're applying that force. And so in both cases, my distance was the radius because it's basically, I'm applying it at this point, which is at the very tip from here, right? So in this case, for this example would be my radius. It could also be that I'm applying a force like right here for a ball. And then in that case, it would be my radius from the force would be a little bit tinier. So I'm just going to draw this out. Basically what you're looking at is this is a bowling ball, and if I'm applying a force that goes this way, then this is my force vector, and this is my r vector, and this is theta. And remember when I mentioned that to calculate theta, you want to take the tails of both. So this is one vector, this is the other vector, and so theta is going to be a 90-degree angle. Sine of theta is just 1, and so it's going to be basically, in this example, the torque is going to be just this, the radius, times the force. And we're going to get this scalar quantity that represents the product of those two. All right, so that's kind of the torque. And then it's important to also know what is the final thing I want to mention about torque is that this is going to be a vector that is the cross product of r and f, and so you need to use the right hand rule to figure out where is the direction in which the torque is going. All right, Newton's laws. So these are pretty high yield too. They're not going to ask you like what is Newton's law first one, but it is important to know these things to figure out answers to physics questions. So the first one is ma equals the net forces on something, and that's where free body diagrams are really valuable because because you're going to be figuring out like what are all these forces that are acting on something. You're going to add the vectors of the forces that are acting on something, and then you're going to figure out, okay, based on this equation F equals ma, what is the mass of the object, what is the acceleration, and what is the net force. And it's important to know that if something is zero, and I mentioned that when I was talking about translation equilibrium, if the net forces of something is zero, that means that that object is either at rest or at constant velocity. It means that there's zero acceleration. Remember, acceleration is the change in velocity over time. The second law is that any acceleration is the result of a net force that's greater than zero, which essentially is F net equals ma. And so this means that if there's a force acting on something, if there's a net force that's acting on something that's not zero, something is accelerating. And then third law is that any two objects that are interacting with each other experience equal and opposite forces as a result of their interaction. So if you remember the gravitational force that I was mentioning, gravity, essentially you are standing on the earth, you are being attracted to the earth. That's why you're not able to go flying, because you're attracted to the earth. The earth is also attracted to you. It's just that the force that you exert on the earth is just so tiny as compared to the earth's force on you. Okay, the next is motion with constant acceleration. And so here, linear motion these are all very important equations that you need to know. And so let's talk about this one. V final equals V0 plus acceleration times change in time. So the way that I think of this is, let's say I go to the top of the Eiffel Tower and I just drop a beanbag. So my first initial velocity is actually going to be zero, because I'm not throwing it downward. I'm just holding it and then dropping it. So this is zero. My acceleration is just going to be the gravitational force. So it's going to be, g, and it's going to be it's going to be downward. And then based on the amount of time that's passed, I can figure out what is the final velocity. And so all I really need to know is how long does it take to reach the bottom, and then I can figure out what was the velocity when it hit the ground. And so that's kind of how you think about this equation. This equation is kind of the same thing. You just do the square. So V final squared equals V initial squared plus 2 times 2 times the acceleration times the change in x. Change in x is a different way of thinking about it, where if instead of telling you how much time it took to get to the bottom, I told you how tall is the Eiffel Tower, and then based on that information you can figure out what is the answer to what was the speed at which the beanbag hit the ground. Okay, change in x, which is the change in distance, equals v initial times the change in t plus 1/2 acceleration times change in t squared. So this is just kind of a different way of putting this equation. You kind of have the same variables, but this time you can use the change in time and the change in distance in the same equation. And then finally, this is the relationship between change in distance and velocity and change in time. So this is a pretty important equation. It's pretty fundamental, which is that, okay, let's say that I'm going at 5 miles per hour, and I tell you that I've walked at that speed for 1 hour, then that means that I've gone 5 miles, and that's basically what this is telling me. And this is assuming that acceleration is 0. And so a different way of thinking about this is that if acceleration is 0, then that's just this equation. These are the same equations. Okay, projectile motion is something that contains x and y components. So if I throw a football in the air, that has projectile motion. And if you assume that there's no air resistance, which is kind of the resistance that air puts when something is moving through it, then the only force that's acting on something that's, like the football that's going in the air, is the gravitational force that's pulling it down. And so the x velocity is going, the velocity of the football is just constant. And the reason for that is because there's no net force that's acting on that football that's in the x direction. The only net force that's acting on the football is in the y direction, because gravity is pulling it down. And so it's important to know that when you're, I guess in this example, when you're throwing a football in the air, there's this speed at which the football is going in the x direction does not change. It's only that in the y direction it's going downward at some acceleration. Okay, inclined planes, there's force components, and so Parallel to the ramp, you use sine theta, and perpendicular to the ramp, you use cosine theta. This is kind of just a little hack that you can use, but you can also think about it and try to figure it out yourself. But basically, if I'm saying that this thing is going downward, we're trying to figure out, well, what is the gravitational force? How do I calculate that? And so since this is kind of sliding down, if I have a gravitational force that's acting on this that goes this way, right? And I want to figure out, okay, what is the force that's acting on it in this direction, and what is the force that's acting on it in this direction? So how you figure that out is, this is the box, this is the gravitational force, and this vector is that gravitational force times sine theta, and this vector is the gravitational force times cosine theta. And so let me repeat that because it keeps disappearing. But this vector is the gravitational force times sine theta, and this vector is the gravitational force times cosine theta. All right, so circular motion, how I always think about this is, let's say you have a rod, and then you have a piece of string, and it's attached to this little ball, and the ball is going around that rod, right? And it's going in circles, and you just kind of hold it, and it's just spinning like that. And so the only force that's really being acted on that ball is this tension of the string that's kind of holding it in. And so even though the ball is going in a circular motion, the only force that's acting on it is the force that's going inward. And so you might ask, why doesn't this ball just collapse inward? And that's because it's technically always going inward, but it's also just spinning. So it is going inward, but by the point that I get to this point, it's now the gravitational force is this way, and so now it's going this way. But now the gravitational force is going this way, so now it's going this way. So it's just kind of always moving in a circular way. And so to figure out what the force is that's going inside the circle, or what is that tension force, it's actually equal to this equation: the mass of the ball times the velocity of the ball squared divided by the radius, or the distance from that center point. Okay, let's talk about energy. So this is not too important, the structural proteins, but it is important to know how joules are derived, the unit for joules. And so how I think of it is, I think of it using this equation. Joules is essentially kilograms times meters over second, and both of those meters over second is squared. And so if you take kinetic energy, which is 1/2 mv squared, this is really important that you know this. If you take the units of this, you take the mass, which is kilograms, and then you take the velocity, which is meters over second, and you square meters over second, you realize that this kinetic energy is represented in joules. And so joules is kind of just a shorthand for representing this kind of complicated assembly of different kilograms and meters and seconds, but joules is kind of how we represent energy. And so energy is either kinetic or potential. You learned about this a long time ago. Potential energy is stored in a system. Kinetic energy is based on movement. So if you have a ball on a hill, this ball over here has a lot of potential energy, but if it's stationary, then it's zero kinetic energy. If it's rolling down the hill, then its potential energy is decreasing, but its kinetic energy is increasing because the velocity is getting faster and faster based on the acceleration. Then we have gravitational potential energy. This is the potential energy based on gravity. And so again, if we have this hill and the ball is at the top of the hill, the gravitational potential energy is calculated by mass times gravitational force times height. And this is again in joules, this thing. And then we have elastic potential energy, electric potential energy, chemical potential energy. So if you were wondering, oh, potential energy, is this just the fact that it's at the top of this hill? There's actually other ways we can get potential energy. You can imagine that if you stretch out this, like, let's see, if you stretch this, you know, the slingy thing, like that, you can, if you stretch it out all the way, then it has a lot of potential energy, because if you take your hands off, it's going to like go really quickly, and all that potential energy gets converted to kinetic energy. So that's elastic potential energy. Electric potential energy, you can imagine something like a battery. It's storing a lot of these charges, like there's a lot of positive charges on one side and there's a lot of negative charges on the other side. And then when you're using the battery, these charges flow from one side to the other. And that's kind of how, very simply, that's kind of how batteries work. And so it's converting the electrical potential energy into energy that you're using to power whatever device you're using. Chemical potential energy is kind of when you have bonds between compounds and then you break those bonds, then you can convert that potential energy into kinetic energy. So you should know the equations for this. So elastic potential energy is 1/2 times K, which is this constant based on, it's called a spring constant, and it's kind of based on whatever material you're using. And then it's x squared, and x is kind of the stretch or the distance from the center point. So if this is kind of how a string is normally, and then you stretch it out like a lot, then x is kind of that distance that you're stretching it. And then you don't need to know equations for electrical or chemical potential energy, but it is really important to know conservative versus non-conservative forces. So conservative forces are these path-independent forces. So you can imagine that if I take a book, right, and I put the book on the bottom of a bookshelf, but then I put it on the second shelf, and then I put it at the top shelf, like the 10th shelf, but then I put it back into the second shelf. The amount of potential energy of this book is actually just the amount of potential energy on the second shelf. It doesn't really matter that I put it from first shelf to second shelf to 10th shelf and then brought it back down to the second shelf. All that matters is where it is right now. But you can compare that to non-conservative forces, and these are path dependent, and they cause dissipation of mechanical energy from a system. So you can imagine that, let's say I have a chalkboard, and I'm using a chalk, right, to write a lot of things. Basically, I'm causing dissipation of mechanical energy from that system by constantly writing and causing friction on that. You can also imagine like air resistance, right? If if I take like this ball and I move it through the air, and let's say there's a lot of air resistance on that day, and I keep moving it around and bring it back down, the amount of non-conservative forces acting on this is dependent on the path, because there's a lot of air friction on this path, versus if I just did this, there's very little air friction, and so the path actually matters. And so those are non-conservative forces. Conservative forces are things like gravity and electrostatic forces. If I take two magnets and I put them right next to each other, and then I move them really far apart, and then I bring them back together, it doesn't really matter that I put what path they went on. As long as they're the same distance apart, they're going to have the same amount of force on them. So that's the difference. That's really important to understand. Now, work is the process by which energy is transferred from one system to another, and it's represented as a dot product. If you remember dot products, that's the FD cosine theta, and it's also just a scalar. It's not a vector, and so you should know that it's F times D times cosine theta, where F is the force, D is the displacement. Power is the rate at which the work is done. So it's essentially this divided by the amount of seconds it takes. So here is joules, and then if we divide that by seconds, then we get kilograms times meters squared divided by seconds cubed, because we're dividing by seconds. Okay, the last thing to know is the work energy system, and this is kind of an important concept to understand, but it's kind of hard to get into your head. And the idea is that when net work is done on or by a system, the kinetic energy will change by that same amount. And so if I'm doing work on something, then I'm basically adding kinetic energy to that system, and if the system is doing work, then I'm basically removing kinetic energy. And so the change in kinetic energy of that system represents how much work is done. Is there work being done by the system or work being done on the system? Okay, mechanical advantage is, if you remember from elementary school or middle school, there's all these simple machines. And so mechanical advantage is the way that a simple machine like a pulley or an inclined plane kind of helps us to do work. And essentially the amount of work that's being done is not changed. It's important to understand that, but the input force of that system is a lot less. And so the best example for this is if I was like an Amazon truck, I was an Amazon delivery worker, and I had to lift this really, really heavy box from here to there, right? That would take a lot of input force. Like I'd have to go against gravity. But if I use this inclined plane, and all I had to do is roll this box up, then basically it's the same amount of work that's being done because the distance has increased. But the idea is that now my input force is a lot less, because all I have to do is just go against just a little bit of gravitational force and just push it along a long distance, right? And so that's kind of the mechanical advantage, is now my F input is a lot less than it was before, where I had to lift this box all the way up this way. So that's what mechanical advantage is. If for an inclined plane, it's important to understand that the mechanical advantage is just calculated by how long is this thing divided by how tall it is. And you can imagine like a really small inclined plane, the mechanical advantage is not going to be that much. Like it might be 1 or something, but here the mechanical advantage might be like 10 or something because this is just so long. So the different types of simple machines, you don't really need to know this too well, but it's inclined plane, wedge, wheel and axle, lever, pulley, and screw. And then the efficiency again is the same as mechanical advantage, which is the F out divided by the F in. And so if you have like a really small F in, then there's going to be a high mechanical advantage. If you have a really small high F out, then this is going to be pretty big. That's the efficiency. Okay, now let's talk about thermodynamics. So the 0th law of thermodynamics is that when systems have the same average kinetic energy, then they have the same temperature, there's no heat transfer. And so I had trouble understanding this when I was studying. And essentially, if you have like these two parts of component, and you have these particles that are moving around, if they're like moving at the same speed and there's the same number of particles, then there's no reason why there would be any heat transfer between these two compartments because they have the same amount of kinetic energy. And that's kind of how I think about thermal equilibrium. It's not really that important that you memorize these if you haven't already. It would be kind of helpful to understand like, oh, Kelvin is Celsius plus 273, but otherwise you don't really need to memorize this. Thermal expansion, these are kind of complicated equations that are just saying a very basic thing, which is that when temperature is increasing, then this object is going to get longer and it's going to get bigger. And so these are just two equations that describe like the change in temperature is directly proportional to the change in volume or the change in length. Okay, now is systems. Systems is kind of important to understand. Systems, you can have isolated systems, closed systems, open systems, state functions, process functions. So let's start with the systems. You can have isolated, closed, and open. The easiest to understand is open. It's when you exchange both energy and matter with their surroundings. So there's kind of there's no like boundary that's enclosing anything. You can exchange heat and matter. Things can go out and energy can go out. Now, a closed system is when matter can't get out. Like, let's say there's a lot of particles in this thing. The particles are not going to leave, right? But like they might get slower over time as they're bouncing around because energy is escaping that system. Finally, isolated systems. Isolated systems are really hard to make in real life because there's no energy that's leaving the surroundings. The energy is always staying in there. And so these particles are not actually going to get slower when they're bouncing around. They're just going to stay at the same speed because the energy is staying contained. They might go slower if their energy is being converted to heat, right? So they might get slower, but now this thing will get hotter. And so that that kinetic energy is just getting converted to heat, but that energy is not getting out of that system. So that's kind of important to understand. Okay. Now we have state functions and process functions. So process functions is the pathway from which one equilibrium state gets to another. So examples is work and heat, right? The work can get converted to heat, but state functions is pathway independent. And so it's kind of similar to what we were talking about before, but this is basically, it's not dependent on the process by which we get there. So pressure, density, temperature, volume, enthalpy, internal energy, Gibbs free energy, entropy, these are not dependent on how we got there. So like the best example is probably entropy. Entropy is like how messy something is. So if your room is really messy and not ordered, then it's high entropy. And so it doesn't really matter how you got there, whether you organized it 10 times or whether you just let it get messy. The entropy is just dependent on that final state that you're in. It's not pathway dependent. But process functions are kind of how one pathway of equilibrium state gets to another. Okay. Let's go to the first law of thermodynamics. So first law of thermodynamics is a statement of conservation of energy. Basically, it's saying that there's a certain amount of energy in the universe. It's not going to increase or decrease. And so the individual system, the change in energy is equal to the energy transferred into that system as heat minus the work done by the system. And so this is kind of a cardinal equation that you should kind of understand why this is true, because it describes how much, this is basically the change in internal energy, and it's equal to the energy transferred into the system as heat minus the work done by the system. And essentially, in the universe, this change is zero. Okay, So heat is the process by which energy transfers between two objects at different temperatures until they reach thermal equilibrium. And thermal equilibrium is, again, when two things have the same temperature. And this is how I remember this is Q equals MCAT. Mass times this constant times the change in temperature represents the heat of that system. Okay, now we have specific heat, which is the amount of energy necessary to raise 1 gram of a substance by 1 degree Celsius or 1 Kelvin. And so the specific heat of water, for example, is 1 calorie divided by grams times Kelvin, and it's equal to 4.184 joules divided by GK. And so it's this is kind of something that's going to come up a lot. And how you use this is they're going to give you, let's see if I can find an example. So this is an example where I found this on the left, the specific heat is low, and on the right, the specific heat is high. And so what you can see is that this is going to heat up easily because it doesn't take a lot of energy to raise this by 1 degree. On the right, it takes a lot more energy, almost 4 times the energy, to raise this by 1 degree. And so that's kind of how you use specific heat, or the Q equals MCAT equation. Okay, the next thing is heat of transformation, and this is how much energy does it take for phase change, so solid to liquid, liquid to gas, and that's represented by Q equals ml, where L is the heat of transformation. Now, this was always a very tough concept for me to understand, which is processes with a constant variable. There's isobaric, isothermal, adiabatic, and isovolumetric. Isovolumetric is when the volume is constant, and so because the change in volume is 0, the work is 0. And we'll keep in mind this equation when we're looking at all of these processes. So work of a gas is equal to negative P times the change in volume. P is pressure, V is volume. And so isovolumetric is the change in volume is going to be 0. And so because of that, the work of the gas is 0. Adiabatic means Q is equal to 0. And so there's no heat that's exchanged from the system. Isothermal is the temperature is constant, and so the change in U is 0. And the reason for that is because when the temperature is constant, that means there's no change in energy inside and outside the system, and so the change in U is 0. And then isobaric is the pressure is constant, so change in P is 0. Okay, so those are kind of, you can kind of understand them from just the word themselves: isobaric, pressure; isothermal, temperature; adiabatic, heat; isovolumetric, volume. And so this is how you can look at these equations. And so if you look at isobaric, the pressure is the same, right? Initial pressure stays the same. Isovolumetric, the volume stays the same, right? The initial volume stays the same throughout. And then we have adiabatic and isothermal. So I think I was always confused between isothermal and adiabatic, especially because the two graphs look pretty similar. You can see that isothermal, the pressure is going down and the volume is increasing, and adiabatic is kind of the same thing. And so the way that I started learning about it is that, let's say that we have this piston, right, that you see in chemistry class, and there's this gas, and then the gas is expanding, and because the gas is doing work on the piston, so this, let's say this is the piston initially, and then the gas is expanding, and so because of that, the piston goes up, and the gas is expanding. And so because of that, because the gas is doing work, it's losing heat, right? And so when it's losing heat, there's heat being exited out of the system. But let's say that we have a heater outside the system, and so this gas is staying at the same temperature while it's expanding. So that's kind of the difference between adiabatic and isothermal. Isothermal, when we're adding heat, the temperature is constant because we're adding heat to the system and it's doing work. So it's losing heat, but we're also adding heat from the outside. Whereas adiabatic is kind of when there's no heat exchange. So as this gas is doing work by expanding, and the gas is expanding, and so it's losing heat, but we're not adding anything. So the gas is losing heat, and it's also the temperature is dropping. And so that's kind of how I think of the difference between adiabatic and isothermal. Isothermal is the temperature is constant. Adiabatic is that the heat is not exchanged. So if there's no heat being exchanged, Q is equal to 0, but the temperature might be changing. Whereas in isothermal, the temperature is constant, but we might be adding heat or taking away heat. Okay, The next thing to understand is the second law of thermodynamics. This is obviously very important, and this is all about entropy. It introduces the concept of entropy, and I already kind of talked about entropy as how much disorganization is there in the system. And so I always had trouble understanding this because I was thinking like, why is this shape more disorganized than this shape necessarily? And it's more about how many different positions can this occupy. And so there's only one way you can get these particles to line up like this. Maybe you can switch around these particles a little bit, but ultimately it's a very organized system. Whereas there's a lot of different ways that you can allow these particles to spread around and do that. So it's basically the number of states that it could be in. So in this one, there's only one state that it could be in. But this one, if you're allowing it to be disorganized, then it can be like all over the place. It can be like whatever position. So there's so many different states. And so that's why this is high entropy. So whenever you think of entropy, you want to think about how many states could that exist in, or how much energy has spread out, or how spread out has the energy become. And so whenever you think about your room, for example, it's really hard to maintain a low entropy state in your room because you have to keep everything organized. But how many different ways can your room be messy? So many different ways. There could be pencils on the ground, or books, or clothes, and so that's a lot of different states for it to be high entropy. So high entropy. In a closed system, there's, for everything up to and including the universe, remember we said the universe we can imagine as a closed system because there's no change. The change in U is 0 in the universe. The energy is spontaneously and irreversibly going from localized to being spread out. And so basically the ultimate end outcome of the second law of thermodynamics is that the universe kind of dissipates into the highest entropy state, which is all heat, because we've kind of we're not able to sustain any low entropy states anymore. Okay, so that's entropy. Now let's talk about characteristics of fluids and solids. So fluids, are things that flow and conform to the shape of containers, liquids, gases. They exert perpendicular forces but not shear forces. It's not too important to know the distinction. Solids do not flow. They maintain their shape regardless of container. Density is the mass divided the volume. And we represent density with this Greek sign. I always forget what the letter is called. Pressure is the amount of force per unit area. So you can imagine that if I'm putting a lot of force onto a very small amount of area, then there's high pressure. But if I put the same amount of pressure over a huge area, then if I put the same amount of force against a huge area, then I'm kind of spreading out my forces, and so it's a weaker force. So pressure is essentially force divided by area. And remember, a gas is kind of like a fluid that goes into its container. And so the pressure exerted by a gas on its container is always perpendicular to the container walls. The absolute pressure is when you add the, so the best way to describe this is kind of with a picture. So let's say that I have this, right? And then I'm kind of trying to figure out what is the pressure on this, right? So basically the pressure is going to be from the air above as well as from this fluid. And so let's say that I have this container and it has fluid, and I'm trying to figure out what is the pressure at this point, right? What is contributing to the pressure at this point? It's going to be the pressure from all this liquid above that point, right? All this liquid above this point is contributing to this pressure, as well as all the gas up here. And so you have to add those two to get this P total. And so P total is equal to P0 plus the density times gravity times height. And so this P0 is equal to the atmospheric pressure that's being added to this. Remember, like all this pressure over here. And then this density times gravity times height is basically, you have this liquid and you're trying to figure out what is the pressure at this point. So you have to figure out how much pressure is this amount of liquid adding to this point, and that's what this is for. So this is essentially saying in water, every additional 10 meters of depth adds 1 atm to the P total. And so the further down you go, you can imagine that there's more pressure being added because there's more liquid above you that's adding pressure. Okay, now we have gauge pressure, and gauge pressure is the difference between absolute pressure and the atmospheric pressure. So in liquids, the gauge pressure is caused by the weight of the liquid above the point of measurement. That's kind of what I just mentioned. So you can imagine taking this, the P total, and then subtracting it by the P atmosphere. And that's kind of how you get the gauge pressure. So if I were just to tell you what is the pressure at that point, and then you knew the atmospheric pressure, you can kind of figure out what is the pressure that the liquid is adding. Next is hydrostatics. So there's Pascal's principle, which is that a pressure applied to incompressible fluid will be distributed undiminished throughout the entire volume of fluid. And essentially it means that, let's see if I can find an example. So the best way to describe Pascal's principle is with this picture. And basically where there's the same amount of pressure at P1 and P2. Basically we apply this force over here, and we're applying this force over a very small amount of area. And if you remember what I was talking about pressure, it's force over area, right? And so if the denominator here, area is small, and the force is, I'm just pushing my hand down, so the pressure is going to be pretty big because the area is so small. And then here, the area is really big, right? And so this area is going to be bigger, and this pressure, P2, has to equal P1, according to Pascal's principle, because the pressure is equal throughout. And so because of that, this output force is going to be pretty high, because my input pressure is going to be the same as the output pressure here, right? If the input pressure is high, P2 is high, A2 is high, right? So A2 times P2, you can imagine that F2 is really high. And so that's why we're able to, just by pushing down with our hand, for example, we'd be able to lift up this car. And so that's kind of another example of mechanical advantage. So that's Pascal's principle. That's always how I remember that. Then we have hydraulic machines, and that's exactly what I was talking about. That was an example of a hydraulic machine. And then there's Archimedes' principles. Archimedes' principle is that when an object is placed in fluid, there's this buoyant force against the object that is equal to the weight of the fluid displaced by the object. And so this is kind of hard to understand until I was watching this Khan Academy video about it, and it explained it really well, which is that when you have all this water, and then you put a ball inside, there's going to be a buoyant force that's pushing this ball upward. And the best way to think about that buoyant force is that this ball is competing with water to be in here, right? There's all this water, and now this ball has pushed up some of the water. And so all that water wants to come back into that space that the ball has occupied. And so the force that the water is putting onto this ball to go back up is dependent on how much water has been displaced by this ball. And so you can see that the force, the buoyant force, is equal to that density of the fluid times the volume. And if you can calculate this is actually just the mass, right, times the gravitational force. And so basically, then that's what this is saying over here. So basically, the buoyant force is equal to the mass of the fluid times the gravitational force, and that's what is pushing this object back upward. Now, the density, this is another important equation, which is just based on what I've just told you, which is that the density of the object divided by the density of the displaced fluid is equal to the weight of the object in air divided by the weight of the object in air minus the weight of the object in water. And so this is essentially saying you don't need to memorize this equation, but you need to understand why it works. Essentially what this equation is saying, it's best to describe this by just giving you two examples. So let's say that the density of our object, the ball that I was talking about, let's say the ball is a bowling ball, and so it's a really high density, like it's very heavy for how much space it takes up. If that density is very high, then what that is telling us over here, this number would be really high. And so what that is telling us here is that the weight of the object in air is going to be really high, right? So it's going to be a heavy object. And that this difference is going to be pretty minimal. So the weight of the object in air is going to be kind of similar to the weight of the object in water, because this has to be pretty close to 1 or 0 for it to be true. But if the density of the object, let's say the object is like a beach ball, right? It's very low density. That means that this is going to be pretty high, right? So the denominator of this is going to be high if this is a low number. And so if the weight of the object in air minus the weight of the object in water is a very high number, that means that the weight of the object in air is very high compared to the weight of the object in water. And so you can kind of reason out what this is saying, which is that the weight of the object in water is going to be pretty low. And that's kind of true of a beach ball. It's not going to be the weight is not going to be very heavy is not going to be very large in water. Versus a bowling ball, the weight of the object in water is going to be pretty big and probably pretty similar to the weight of the object in the air. That's what basically this equation is saying. You don't need to memorize it, but just if you can understand that reasoning, that'll be helpful. If the max buoyant force is larger than the force of gravity, then the object's going to float. So that makes sense. So if this force is greater than this force, then it's going to float. But if the buoyant force is lower than the force of gravity, then it's going to sink. So that's just kind of self-explanatory. And then that's what this is saying too. Okay, next is specific gravity. Specific gravity is the ratio of density of an object to the density of water. And so if I told you that, a bowling ball has a density of 4 and water has a density of 1, then specific gravity of that object is 4. Cohesive versus adhesive. Fluids have cohesive forces with other molecules of the same fluid. So cohesion is like why water forms droplets, because they're all cohering to each other. And then adhesion is that it sticks to other materials. So that's why water sticks on a window shield, for example, because it's adhering to the window shield. Surface tension, because of cohesion, these water molecules are sticking together, and that's why crickets are able to walk on water. I forgot which insects are able to. That's why, because there's surface tension. Okay, hydraulic lifts. This was the example that I was giving you with the hydraulic machines and Pascal's principle, which is that if you have a force that's being applied here, and then this force is being applied here, the pressures throughout this liquid, because it's continuous, has to be the same. And so this output force, F2, is going to be really high, even if this F1 is not that high, because the area is just so much larger here. Okay, the next is fluid dynamics. We have viscosity, laminar flow, and tubular flow. So viscosity is how much internal friction the fluid has. A viscous drag is a non-conservative force generated by viscosity. And actually in med school, one of the things we learn about is all these different diseases and autosomal dominant diseases that are caused because blood just gets so viscous, and that causes like strokes and things like that, because there's not enough blood getting to the brain and things like that. So that's kind of the medical connection to this. Laminar flow and tubular flow. Laminar flow is smooth. Turbulent flow is kind of like an airplane. When it's really rocky, it's very rough and disorderly. Puiseux's law, I've never known how to say this, but it basically determines the rate of laminar flow. So it's assuming that it's smooth and orderly. If there's a lot of bumps and edges, then you can't use this law. But basically it says that Q, which is the flow, is equal to pi times the radius. So radius is, you're assuming that this is going through like a blood vessel or some rod, right? The radius is the distance from the center to the edge, times the change in pressure, equals 8 times this density times L. So the equation is Q, which is flow, times pi times, Q, which is flow, equals pi times radius to the 4th times change in pressure divided by 8 times a constant. This constant is dependent on the viscosity of the fluid, so it's dependent on the fluid at hand, times the length at which you're looking at. And so that's what this law is equal to. And the relationship between radius and pressure gradient is inversely exponential to the 4th power. And what that means is that if somebody asks you, like, if the blood vessel gets larger, does the pressure gradient get smaller or larger? And the answer is that the pressure gradient gets smaller, because they're inversely proportional. So radius really affects how much pressure gradient there is. This P initial is going to be larger than the P final. So there's less pressure at the final pressure than the initial pressure. And that makes sense, because you need a lot of pressure to get it from here to here. And so that's why fluids flow from high pressure to low pressure. Okay, now we have flow rate. Flow rate is flow, Q, is equal to volume divided by time. So basically, if we're looking at a blood vessel, how much blood is getting across this in a certain amount of time. A is the cross-sectional area, and V is the velocity. So another way to measure this is what is the cross-sectional area of that blood vessel times what is the velocity of blood that's going through that cross-section. Okay, now we have the continuity equation, and continuity is basically saying that we're going to have the same flow rate throughout the entire blood vessel, for example, or the entire pipe. So if this is a pipe, and then it's getting larger over here, the flow is going to be the same over here as it is going to be over here. And so you might ask, like, how is that possible? And the reason that's possible is because the velocity is really high over here, and the velocity is really slow over here because it gets so wide. And so V1 over here is really high, even though A1 is very small. And then V2 over here is very small because A2 is really large. And so there's basically continuous flow throughout entire blood vessel, or entire, like any form of laminar flow will have continuous blood flow. Okay, Bernoulli's equation is basically that the sum of static pressures and dynamic pressures is going to be constant between any 2 points in a closed system. And so basically this is going to equal this. And I think it'll make more sense as we go on, but I will come back to this and explain this as we go through more terminology. Okay, so this is basically the best image I found for Bernoulli's equation. And you can see, let's say that I took a point right here, and I took another point right here, okay? The first thing I want you to notice is that this and this are going to cancel each other out, because the potential energy at this point is equal to the potential energy at this point, because the height of height 1 and height 2 are equal. So that makes it really easy, because these two heights are equal, we can cancel these two out. And so now we're looking at P1 and then the velocity 1 as compared to P2 and the velocity 2 to figure out the energies. And remember, because this is a single system with laminar flow, we're allowed to use this equation. And so there's some force that's being applied here that causes P1 to have to be greater than P2, and that's why the liquid is flowing this way, right? Because it's going down its pressure gradient, and so because of this force, P1 is going to be higher than P2. But let's first focus on V1 and V2. Where do you think the fluid or blood is going to be moving faster, at this point or this point? It's probably going to be moving faster at this point, because if you remember, Q equals AV, right? And we know that Q is going to be the same throughout this entire thing. And so because this A is much smaller, that means V2 is going to be much bigger. And so this V2 is big, right? And this V1 is small. So that's kind of how you can think of that. And we know this P1 is going to be bigger than this P2. And the reason for that is because there's forces that are acting this way and pushing this blood this way, whereas there's less force that's being applied this way to this object and moving it this way. So to reiterate what I said, A2 is smaller than A1. This A1 obviously is bigger. V2 is greater than V1, and that's because this A2 is small. So V velocity is really high here. And the final thing is that the pressure at this point is higher than the pressure at this point. Okay, and that's why fluid is flowing this way, because it's going down its pressure gradient. And remember, Bernoulli's equation is basically saying this is equal to this. Okay, the next thing to talk about is the Venturi effect. The Venturi effect is that velocity of a fluid going through a constricted area will increase and static pressure will decrease. And that's kind of what we just mentioned, which is that as we're going from this really wide thing to this really narrow thing, basically the velocity is going to increase because this area is decreasing. And then the static pressure is decreasing, and that's because it's going into this, and we know fluids goes down this pressure gradient. So it's going from high pressure to low pressure, low speed to high speed. Okay, the next thing to know is the Venturi tube, and I'm going to show an image of this to make it more understandable. But basically we know A1 over here and we know A2 over here. So what do we know based on that? We know that the velocity is going to be really high over here as compared to over here. Okay, then we know that we're looking at this point and we're looking at this point. So we know that the heights are equal, and because of that, the density times gravity times height is going to be equal at both points. So because of that, because we know velocity is higher here, we know that the pressure must be higher here. And so that's why, because the pressure is higher over here, that's why this is elevated, because there's more pressure, versus at this point this is less elevated because there's less pressure. It's moving more this way. And so that's why this fluid is sticking up. And you can figure out the pressure difference by just calculating this height and multiplying it by the gravitational force times the density of the fluid. Okay. Now we have fluids in physiology, and this is the circulatory system. The circulatory system behaves as a closed system with non-constant flow. The non-constant flow is our pulse, and so this is kind of what I've been alluding to by talking about our blood vessels. V is velocity, Q is the flow, and then area, A is the cross-sectional area. This is the equation we just looked at. And then now is where we kind of compare this equation with this equation. So we know that the change in pressure is equal to the flow of the fluid or the blood in our body times R, which is the resistance. And in our body, the way that we get resistance is based on these arteries and arterioles that are kind of constricting and expanding, and that's how we get resistance. So here, this is basically saying that our pressure change is equal to the flow times the resistance. And so another way of putting that is by taking this equation, the VA, and then putting that in the Q, and so we get VA times resistance. And so pressure is directly related to velocity, area, and resistance. Area is inversely related to resistance and velocity, and then as our cross-sectional area increases, so this guy, the A, then that means our resistance is decreasing and or the velocity is decreasing. So as this goes up, this and this must go, this or this must go down, the V or the R. Okay, next we're talking about breathing. And again, these are all clinical correlates of physics. So these are kind of the ways that they'll test you when you're reading the article. So breathing, basically inspiration and expiration creates pressure gradients, not only for the respiratory system, but for the circulatory system too. And so you can imagine that when you're breathing in, your diaphragm is going down. And so in the respiratory system, basically your lungs are getting larger, and that creates a pressure gradient where your lungs, because your diaphragm has gone down, your lungs have expanded and there's less pressure in your lungs. And so the higher atmospheric pressure goes into your lungs because now your lungs have expanded, there's less pressure, and so you're breathing in. And then when you're breathing out, your diaphragm goes up, you have more pressure in your lungs than outside, and now your air is going out. And so that's how breathing works. Alveoli are these little things in your lungs that allow for gas exchange, and air at the alveoli essentially has zero speed. Okay, next is electrostatics and magnetism. Electrostatics and magnetism is a very high-yield concept in physics. So let's talk about charge. Coulombs is the SI unit of charge. We have protons and electrons, and we've made it really simple because we have this thing called, that we just say as E, and that kind of represents the charge that a proton or electron has, and it's equal to 1.6 times 10 to the negative 19 coulombs. And so both protons and electrons, fortunately for us, has the exact same fundamental unit of charge. Attraction and repulsion is, when you have a proton and electron, they attract. When you have an electron and electron, they repel. Things that have opposite charges attract. Conductors and insulators are also important in circuits. Conductors allow electrons to move, and then insulators don't allow things to move in a circuit. They resist the movement of charge, and will have localized areas of charge that do not distribute over the surface of the material. Okay, now we have Coulomb's law. Coulomb's law is that you have the magnitude of electrostatic force between two charges. And so if I have a proton and a proton, then these two things are going to go apart from each other, right? And what is that force called? That force is given to us by Coulomb's law, which is this. So it's this constant times Q1, the charge of the first particle, times the charge of the second particle, divided by the distance between them squared. The electric field, another thing that I always got confused about was this R. Like, does this R mean half the distance or the full distance? It means the full distance. So this particle and this particle, the R is the full distance between them. Electric field is basically, if I have a proton over here, right, it's going to generate an electric field around it. And the electric field is basically telling me what happens if I put another particle over here. And so the electric field is answering that question by telling us, oh, this proton over here is going to cause this force on this particle if you put it over here. And so the electric field is basically this imaginary field around a particle that tells us if we add a positive charge, like a proton, around this particle, what's going to happen to it. So if I put a proton over here, oh, this force is going to push it away. If I put a proton over here, oh, this force is going to push it away. If I put a proton over here, oh, this force is going to bring it this way. So basically, electric field tells us if I add a proton to this field, where is it going to go? So in this system, I have like an electron and a proton. So if I put a proton over here, where is it going to go? It's going to go this way. If I put a proton over here, where is it going to go? It's going to go that way. So that's what an electric field is. A very simple explanation of electric field. So how you calculate what the electric field is you just do the force divided by the charge. And so then you get KQ divided by R squared. And I always used to get confused by what is this Q value over here. And basically it's just telling us that, oh, if I have a proton over here, what's the electric field? Well, the electric field is just going to be this this particle, you take that charge. Okay, to find the electric field, all you have to do is to take the force that's exerted on that test charge. So if this is the charge that's creating the electric field, right? And we have all these lines that are the electric field. And then we have that other charge over here. We kind of just ignore this charge, the electric field is just dependent on the charge that's creating that electric field. And so all we have to do is just take what we would calculate as the force between those two charges and then divide that by the charge that we're kind of ignoring here. And so the electric field is just K times Q, and this Q, remember, is just the charge that is creating the electric field divided by the distance between the two charges squared. So that's how you calculate the electric field. Now, the next thing to know is field lines, and we just talked about this. And field lines show the activity of a positive test charge. So if I put a positive charge, that's the direction. The field line tells us the direction that positive charge would go in. Okay, equipotential lines are just if we draw a parallel line to our electric field lines, that's how we get equipotential lines. And this is an equipotential line. Okay, these are equipotential lines. So remember, this is the electric field line over here that is pointing out from the positive charge in the middle. But then these are electric equipotential lines, which are perpendicular to those electric field lines. So these circular things around, and basically what that's telling us is that at all these different points along these equipotential lines, there's the same amount of potential that a charge has. And so to move a particle from here to here, it requires no extra work. But to move a particle from here to here on different equipotential lines, that takes a lot of work because let's say this is a positive charge. To move that positive charge so much closer to this other positive charge, that's going to take a lot of work. And in the same way, if we take a particle and we move it away, right, to a different equipotential line, then there's going to be work done by the system because it the positive charge likes to be out here away from the other positive charge. So that's kind of what equipotential lines are. Okay, the next thing to talk about is electric dipoles. And electric dipoles are just when you have a positive charge and a negative charge right next to each other. And basically all this is saying is that there's going to be a net torque on this dipole when it's situated in an electric field. So let's see if I can find an example. So here's an example of what that is talking about, which is that this is a dipole, right? There's a positive particle here and there's a negative particle here. And this is situated within an electric field, and the electric field lines are all pointing this way. And so what's going to happen is that when there's a dipole in an electric field, the dipole actually doesn't move translationally, like it doesn't move this way or this way. What actually happens is that there's just torque on it, and so the electric field is just going to move this way because this is the positive charge and this is the negative charge. And so that equation that we were looking at before over here tells us, well, this equation over here tells us what is that torque going to be, and that torque is equal to this P over here is just the vector that is created by the dipole. So it points from one of the charges to the other charge, and this is the electric field that it's situated in. And so it's just the cross product of that, and that describes the torque that we have. And remember, this torque is a vector. The other thing is this equation, which is the voltage. And this is just describing, well, what is that? So here I've just pulled up an interpretation of that equation, and essentially it's just the electrostatic potential due to a dipole. And so V, just like normal, is the potential, the electric potential, and K is the Coulomb's constant, Q is the magnitude of the charge, D is the distance between the charges, and R is just the distance from the dipole to the point at which the potential is measured. And so by that you could get the voltage of a dipole. Now the dipole moment is just very simple. It's just the distance between the two charges times the charge itself. Okay, now these are the important equations that you need to know for electrostatics and just electrostatics actually. And we've already talked about force. We've already talked about electric field. This is electric field. This is force. Now this is electric potential, KQQ over R. So just remember that the difference between this is that there's no R squared. And then we have voltage. And voltage is what we're going to talk about next. So just know these four equations. They're all interrelated and all very similar. The next thing is electric potential energy. So electric potential energy is the amount of work required to bring the test charge from infinitely far away to the given position. So to give you an example, let's say I have this charge over here, this positive charge, and then I have this positive charge all the way out here at infinity, right? The electric potential describes how much work is it going to take to bring that charge right next to this positive charge, right? And so that's what electric potential energy is. Because these forces don't like to be next to each other, this is going to repel. So the fact that they exist close by to each other means that there's some potential energy. And if we release these two charges, then they're going to go flying away from each other. And that's why there's electric potential energy when two positive charges or two negative charges are right next to each other. This is the equation again. KQQ over R is the equation for electric potential energy. And next we have electric potential energy. So electric potential energy is what I just described. And electric potential energy is related to voltage, because if you just take the electric potential energy and divide it by that charge, then you get voltage. Now voltage is just the potential difference from one spot to another spot. And this is how batteries work, is that there's going to be a voltage, there's going to be a potential difference in these two places. And because of that potential difference, there's movement of charges from one place to another. And because there's movement of charges within a battery, or because a battery has potential, when you add that battery to a circuit, then everything lights up, because now suddenly the battery is allowing charges to move from high potential to low potential. So within your battery, you have an area of high potential and you have an area of low potential, right? And these two are just separated by a little bridge. And then you have a circuit. And now all these charges go from high potential to low potential, or from low potential to high potential, depending on whether we're talking about negative test charges or positive test charges. Positive test charges go from high potential to low potential, and negative test charges go from low potential to high potential. Not that important that you know this, but very important that you understand voltage. Voltage is the difference in voltage can tell you about the work that is being done. So the work from point A to point B divided by the charge is equal to the voltage difference. And that's basically how batteries work in circuits. Okay, the next thing to talk about is magnetism. And with people who have tutored, magnetism is the thing that really trips a lot of people up. And the reason for that is because a lot of people think that electric fields and electric forces point in the same direction as magnetic fields and magnetic forces, but that's not true. And I'm going to talk about magnetic field. Okay, this is a magnetic field, right? This is a electric wire, and essentially any moving charge, so let's say this is a proton, and it's moving. So if a proton is moving this way, then it creates an electric field around, it creates a magnetic field around it. So we know that protons already create electric fields, right? And this electric field is going like this. Well, if it's stationary, there's no magnetic field. But let's say this proton is actually moving. If it's moving, then it creates a magnetic field as well. Negative charges also create magnetic fields if they're moving. So now let's talk about this wire. Now this wire, let's say that it's moving this way, and these are the electrons that are moving up. Now we can use the right hand rule and figure out, well, which direction is the magnetic field in? And essentially we point our thumb in the direction that the negative charges are moving in, and then you wrap your right hand, and it's going to look different because my camera is inverted, but you do this by yourself. Take your right hand and then just curl your right hand around, and you'll figure out what is the direction in which these magnetic field lines are moving, and that's how you figure out the magnetic field. So if you look at this example over here, this is the same thing, which is that we see which direction is our current moving in, and then we figure out, okay, based on the right hand rule, I can figure out which way is these magnetic field lines going. Okay, so it's all dependent on current. Just remember which way electric current is going. So one really quick correction I want to make on something I just said is I described this current moving and how that creates the magnetic field. So this current represents positive charges that are moving this way. And those positive charges, then you use the right hand rule, and then you figure out what is the direction of these magnetic fields that is created by that wire, by these positive charges moving. But if we were told that electrons were moving in this direction, then this magnetic field would point in the opposite direction. So the current represents the positive charges that are moving. That always confused me prior, and I just want to make sure that you guys understand that. So that was a quick correction. Okay, the next thing to talk about is these two equations. They're not going to show up too much, but I would just try to remember them, which is that this is the magnetic field that is created by a straight wire, and this is the magnetic field that is created by a loop of wire. And I can show you a loop of wire magnetic field, which is that it would look like this, where yeah, this is a good example, where you have this loop of wire, and there's a current that's going through it, and because of that there's going to be a magnetic field that's created by that loop of wire. Again, not too high yield, but that might come up. Okay, the next thing is diamagnetic materials, paramagnetic materials, and ferromagnetic materials. Now ferromagnetic materials, iron has a lot of is very magnetic, right? So you can kind of know based on that it's going to be strongly magnetic. There's some unpaired electrons. Diamagnetic has no unpaired electrons and are repelled by a magnet, and then paramagnetic are in the middle. They have some unpaired electron and they're weakly magnetic. Now we have characteristics of magnetic fields. Now characteristics of magnetic fields, it's important to know that any moving charge can create a magnetic field. So in addition to that, external magnetic fields also exert forces on charges that are moving in any direction. So let's say I have, I told you that, okay, I have this really strong magnet and it's causing this magnetic field, and this magnetic field is represented by these X's. And I remember being confused in physics class by these X's and dots, and X's basically mean that the magnetic field is going into the page, and dots mean that magnetic field is going outside of the page. So again, let's say that the magnetic field is all X's. If there's a electric charge like a proton that's moving through this magnetic field, then there's going to be a force that's acting on that moving charge. Okay, so let's say the moving charge is moving downwards and it's within a magnetic field. Now there's going to be a new force that's acting on, sorry, these should be X's. Now there's going to be a new force that's acting on this moving charge. And so now this moving charge might move in a slightly different direction because it's within this magnetic field. So I think it'll be easier if I show you an example. This is a good example of what I'm talking about. So let's say that there's this magnetic field, and again, X's mean that the magnetic field is going into the page. So remember that this is the magnetic field, and this magnetic field is created already. It's not from these moving charges. These moving charges are now moving within this magnetic field, and let's say that this positive charge is moving this way, so up and to the left, within this magnetic field. Now, there's this equation, and the equation is represented by QV cross B, and that represents the magnetic force that's acting on this particle within this field, and it's dependent on the direction that this particle is moving. So let's do the cross product of the velocity, which is in this direction, with the magnetic field, which is again going into the page. And I want you to do the right hand rule, and remember it's kind of the opposite with my hand because my camera is inverted, but you take your right hand and you point it in the direction of the velocity, so it should be going up and to the left, and then you curl your hand into the page. And what you should get is that the positive charge points in this direction. Okay, now remember when I mentioned that these are always for positive charges? So when you're talking about negative charges, like when I was talking about the current in the wire, you represent that as positive charges that are moving through it. And if you have a negative charge that's moving through it, then you just reverse the direction. So the same thing goes with this force. So now we have a negative particle and it's moving in this direction. So again, use your right hand rule, point your hand in the direction of the velocity, and then point your hand into the page. And then you point your hand, and your hand should be pointing up. And so if this was a positive charge, it would be, the force would be pushing it upward. But instead, the force is pushing it downward because it's a negative charge. And so that's just kind of a helpful way to understand which direction is the force pushing this moving particle in. Okay, so again, that's the moving point charge. And then the same thing goes for a current carrying wire. If you have a wire and it's within a magnetic field, there's also going to be a force on that. And let me see if I can find an example for you. Now let's take this as an example. So we have two wires and they're parallel, and both of them have electric currents that are pointing in the same direction. So you should be thinking, okay, based on the right hand rule, I know that this is going to move in this direction, this magnetic field, and this is also going to move in the same direction, right? Okay, so based on that, we should know that when this let's say this first wire is exerting a magnetic field on this second wire. So this second wire, the current is moving upward, right? So that's our V, our velocity, or I should say our I, right? And remember, our equation, if I go back, is IL cross B. So we want to take IL and then cross it with B. And so we take I, which is this is our I vector, and then L, and then cross it with B. And our B vector is again this one right here. If you map out where this is, when you get to this point, it's moving in this direction. So if we do the right hand rule, then we get what this guy is showing over here, which is we point our hand upward, we curl it in, and we see that this is pointing to this way. And if you do the same process with this wire, you'll see that this points this way. And so basically when you have two wires that both have current moving in the same direction and both wires are parallel, those wires are going to come together because there's a force that each other is attracting to itself. So that's kind of how you can think of wires. And if you can remember that, then it'll be pretty easy to remember these two equations. So just remember these two equations and you'll be solid. And remember, these are just cross products between QV and B, and this is a cross product between IL and B. Okay. The next is Lorentz force. You don't really need to know this, but it's the sum of the magnetic and electric forces acting on a body. It's like a free body diagram, but instead of translational forces, it's electrical and magnetic forces. Okay, the next thing to talk about is charges, and then we get into the fun stuff, which is all these circuits. So charges. We have current. Current is, again, the movement of charge that occurs between 2 points of different electric potentials. Remember, current is what happens in a circuit. And current, again, this is where I always used to get tripped up, and that's why I made that additional segment where I was talking about my mistake, which is that current is defined by the movement of positive charges from high potential to low potential. In reality, it's electrons that move in the circuit, but the way that, for some reason, somebody decided that we will think of current as movement of positive charges. So it's just kind of a semantic thing of how we decide to define what current is. So current is defined by the movement of positive charges, but really what's happening in a circuit is electrons are moving, not protons. Okay, and then how do we define current? It's basically how many charges are moving through some point over some amount of time. So in 1 minute, if we have like 1,000 electrons that are moving through a point, then that's how we define what the current is. So current is I. Okay, conductive materials. So you should know that there's conductors and there's insulators. So metallic conductors allow the flow of current. Electrolytic conduction, means the movement of free ions under electric field. And then finally we have insulators. Insulators are materials that don't have a current. So it's really important to know metallic conduction and insulators. Electrolytic conduction is not that high yield. Okay, Kirchhoff's laws are basically, these are very high yield. It's probably going to show up at least once in your exam, which is that the current that's going into a junction is equal to the current that's leaving a junction. And we'll go into an example. I'll show you on Google Images an example. And then we have the loop rule, which is that the sum of all the voltage sources equals the sum of the voltage drop. So this is V source equals V drop. And so let me show you an example on Google Images. So this is a good example of what I'm talking about in Kirchhoff's law. So the current law is essentially that the current that you're entering a junction with is the same as the current that you're leaving the junction with. So this I total over here is equal to the I total over here, because this is what's coming back after you're done with all the junctions, and this is what you're going into the junction with. Now the current gets split up over here and over here when you get to the parallel circuits, and then when it comes out of these parallel junctions and comes back, it sums up and it comes back to I total. So I1 plus I2 equals I total, which is the same as what you started with in the circuit. Now, how do you know how much of current goes in this part and how much of the current goes in this part? Well, it's just dependent on the resistances of those two parts of the circuit. And so that's kind of, you take the voltage and then you divide it by the resistance and you figure out the current over here. Now, in this example, it's just a series, it's not parallel. And so the current stays the same throughout the circuit. Now, what about voltage? What happens to voltage? This is kind of a good example of what Kirchhoff's law is saying, which is that the drop in voltage across this, and then across this, and then across this, and then across this, after you add up all the voltages, you get the total amount of voltage, right? And then the drop in voltage is equal to 0. So if I start out with 9 volts, and then I use 2 over here, and then 3 over here, and then 3 over here, and then 1 over here, then that's what Kirchhoff's law is saying. You're not gonna have any leftover voltage in the circuit. All the voltage will be used. If you only have one resistor in the whole circuit, then all of that 9 voltage is going to be used in that one resistor. So that's what Kirchhoff's law is. Okay. Again, make sure you know that that's pretty high yield. Now, resistance is the opposition that a substance offers to flow of E. Resistors are, you can think of them as conductive materials with a lot of resistance that slows down electrons without stopping them. Because if you stop the circuit, then there would be no flow. But there is some flow. It's just that it's creating resistance in our circuit. And this is kind of how you figure out resistance. It's you're not going to have to calculate resistance, but it is helpful. They might tell you like, oh, if we increase the length, then what's going to happen if we increase the cross-sectional area? So just know cross-sectional area is on the bottom, length is at the top, resistivity is at the top, and that's what describes resistance. Okay, Ohm's law is super, super high yield. Make sure you know that V equals IR, and that's kind of how you figure out how much voltage drop is happening across each resistor. Okay. If you add up all the resistance in series, then you get the total amount of resistance. And then if you take the reciprocal of the resistance in parallel and you add them up, then you get 1 over the total resistance. So I was always confused about this until one day somebody much smarter than me in our physics class asked, well, why does resistance drop when you go in parallel? Why is the total amount of resistance in this circuit less than if there was just one resistor? And the reason for that is my physics teacher explained, like, imagine that there was traffic and it was going through a traffic jam, but instead of just one row like there was in series, now you have 3 options for the cars to go. Well, obviously the cars are going to go a lot faster because now cars are going across 3 different places. And so that's why the total resistance in a parallel circuit is less than the resistance if you just, like, let's say that this resistance was 200, this resistance was 300, this resistance was 500. If you just had this total resistance might be like 50. It's going to be much less than these 3 resistances. And the reason for that is because the traffic of the electrons can now go in any one of these, and so there's going to be a total less amount of resistance. So that's how you can think of parallel circuits. Okay, now you have capacitors and capacitance. Okay, capacitors have the ability to store and discharge electrical potential energy. So let me show you an example. So capacitors are kind of, they look like this, but in a circuit, what they'll look like is like this thing, like two lines, and essentially it flows through this capacitor freely, but it'll store charge, so it'll kind of act like a battery where there's voltage difference on that capacitor. And what you'll notice is that there's a series of equations to determine what the capacitance value is. And so capacitance stored that voltage that's coming from a battery, and then they discharge that electric potential energy when they need to. And so capacitance, this is the really important equation over here, which is C equals Q divided by V. V is the voltage difference across the plates, and Q is that charge that's being built up. So if there's a +9 on one side and then a -9 on the other side, Q is 9, where 9 represents kind of like the electrons and protons that are building up on one side. Okay, it's really important to know that the greater the area, the greater the capacitance, the greater the distances between these two plates, the smaller the capacitance. And that's what this equation is telling us. This constant over here, the E naught, that's based on the material of the capacitor. Okay, electric field in a capacitor is equal to E equals V over D. This is also a really important equation to know. So they might ask you, oh, what's the electric field that's created by the capacitor? And it'll be equal to the voltage that's created by the capacitor divided by the distance between the two plates. Okay, now we have potential energy of a capacitor. This is also important, and that's equal to U equals 1/2 CV squared. So that's important. C is the capacitance, V is the voltage. Okay, now it's important to know, and we'll go into this, that these act the opposite as resistors in series and parallel. So parallel is they create a larger capacitance, and series they create a smaller capacitance. Finally, there's that K constant, the dielectric constant, and this just tells us that insulators, when they're placed in between the capacitor, so let's say I have an insulator right in between this, that's going to increase the capacitance by a factor called the K factor, or the dielectric factor. And so the way that you can think of that is before there might be an electron that can fly from here to here in the capacitor, right? And that means that this capacitance is not as strong because it's trying to create voltage difference across these two plates, but some of the electrons are flying. But then imagine that you put a resistor in between those two plates, right? Now there's not going to be as many electrons that are flying, and so now you can have a stronger voltage difference, and that's kind of how you can think about why insulators between capacitor plates can increase that capacitance. Okay, now there's meters. These are the things that you used in physics lab to kind of measure, the volt, to measure the resistance, and to measure the current, and that's what those do. So ammeters have negligible resistance. They measure the current, and you have to put them in series. And why do you put them in series? Remember the Ohm's law that I was talking about. Now there's voltmeters. Voltmeters you have to put in parallel, and that helps you measure a voltage drop because they have very large resistance. So remember, when you're going into a junction, this is kind of what's going on with the voltmeter. You basically put the voltmeter right here, and then you can figure out what is the voltage drop across this. That's again because of Ohm's law. So make sure you understand this according to Ohm's law. If you understand Ohm's law, you should understand why this is in parallel and this is in series. And finally, you have ohm meter, which is to insert it around resistive element, and that measures resistance. So just know those are kind of just vocabulary terms, but make sure you actually understand this connection to Ohm's law. Okay, next is capacitors in series and in parallel. So capacitors in series, remember I told you that when you have it in series, it does the opposite of resistance. So this is kind of looking like this in parallel, where you take the reciprocal, you add them, and you get the reciprocal of that, and that gives you the total capacitance. And here it's just the opposite. You add up the capacitance when you're in parallel, and that gives you the total capacitance. So I just kind of remember that it's the flip-flop of resistance. If you remember that, you'll be fine. Okay, the next topic is waves and sound, and I really like this topic. So transverse waves is kind of like light. It's when you have oscillations of a wave particle perpendicular to the direction. So this is actually what transverse waves look like. And this is not to overcomplicate it, but light has, remember, those dual properties of particles and waves. So this is specifically referring to that wave-like property. And mostly when you think about waves, it's going to be kind of like this, where it's like sine waves or cosine waves. These are transverse waves where they have oscillations, and they're perpendicular to the direction of the movement. Direction of movement is this way. Okay, next you have longitudinal waves, and longitudinal waves is like sound. So this is a longitudinal wave, and this is a transverse wave. So this is kind of like how sound moves, which is that there's just a lot of these particles, and they're bouncing off each other. And that way, they move this way because the vibrations will eventually go from where the sound originates to your ear. And that's what longitudinal waves look like. This is what transverse wave looks like. Okay. Next we have all these equations. This is very important for you to know. You should know that wave speed is equal to frequency times wavelength. And then you should know that frequency is kind of how many of these waves happens per second or per unit of time. And then the wavelength is how long are these waves, right? And you measure it from like crest to crest or trough to trough or any point to the next point. So that's how you measure wavelength. Okay, the next thing is this equation over here, and basically you don't need to know, they're not going to ask you like specific values of this equation to plug in, but it's kind of important to understand what the meaning behind this is. So B is bulk modulus, and what that means is this is basically saying wave speed. So the best way that I always remember this is that in the first grade my teacher asked us to put our head to the desk, and then we had to knock the desk, and I remember it being really loud when I put my ear next to the desk versus when I just knocked the desk and my ear was in the air. It was a lot less loud. And so the way that I remember that is that the bulk modulus, this gets bigger when we go towards a solid and smaller when we go towards a gas. So that's this thing. But then within that material, so when we're in a solid, the less dense that solid is, the greater the wave speed is going to be. So that's kind of counterintuitive because solids are greater density than gases, but you want to know that if I'm talking about a solid, then this numerator is going to be high. But if I'm talking about if I'm talking about a solid that's not at all dense, then this denominator is going to be low, and so this wave speed is going to be high. So the gases have the least amount of wave speed, solids have the most amount of wave speed. Once you get to a solid, the least dense solid will have the greatest wave speed. So that's how you think of that equation. Displacement is how far a point is from the equilibrium position. So if I was like right here, this would be the displacement. The displacement is greatest at the crest and trough, and that's what the amplitude is referring to. And then you have amplitude, which is the maximal displacement, what I just talked about. Then we have wavelength, which I just talked about, frequency, which is the number of cycles per second, and then you have angular frequency. This is kind of just the angular displacement per unit of time, and that's just a different way of representing it, which is 2 pi divided amount of seconds, or 2 pi times the frequency. Okay, then you have period. Period is just how number of seconds that it takes to complete a cycle. So it's the inverse of frequency. And then we have interference. Interference is kind of how these waves interact with each other. So you can have constructive interference where you have two waves and they kind of look similar, and so they just add up with each other. Or you can have destructive interference where you have two waves and they're kind of out of sync. And so when you add them up, then they're just kind of sum up to something less than the sum of the parts. So destructive interference might end up in like these smaller waves, or it might just end up in a straight line. And so that's kind of the destructive interference versus constructive interference. Now you have partially constructive and partially destructive interference. So destructive interference, the way that they're describing it is that it results in just a straight line. Partially is that when you have it's kind of out of sync, but it still ends up in some waveform, right? And so you might still have it might not be a straight line if you add these up, but you'll have a little bit. Okay, traveling waves versus standing waves. So traveling waves, you have continuously shifting points of maximum and minimum displacement, and standing waves is just when you have constructive and destructive interference of two waves with the exact same frequency traveling in opposite directions. So standing waves, you're going to have perfect destructive interference, versus traveling waves, you'll have shifting points of maximum and minimum displacement. Let me see if I can find you an example. So this is a good example that kind of explains what I was saying. A standing wave is kind of like this, where it doesn't move, it's just kind of stationary. And then traveling waves, you can see a video of this, but traveling waves, it's kind of going up and down and up and down and up and down. So then it might look like this after that, and then it might look like this for a second, and then it'll look like this. It's basically traveling. So that's what that difference is. Okay, so again, traveling waves have continuously shifting points of maximum minimum displacement, and standing waves is just the same frequency traveling in opposite directions in the same space. Antinodes and nodes. So nodes is where there's no oscillation, antinodes is where there's maximum oscillation. So if we're looking at this wave over here, this is the node and this is the antinode, because if we think about this as a traveling wave, then this is one point and then this is another point and then this is another point. So you can see no matter how it's going, like if we take two parts of a string and we like move it up and down, no matter what, this place is always changing its amplitude, and these things are not changing. So that's what node and antinode means. Then we have resonance. Resonance is the increase in amplitude that occurs when a periodic force is applied at a natural resonant frequency. And we're going to go more into resonance in a little bit. But yeah, just understand like resonance is kind of related to what we'll look at over here. Okay, damping is the decrease in amplitude that's caused by an applied or non-conservative force. So that's also something that we're going to talk about in a little bit. Okay, the next thing is sound. So sound is, they'll try to connect it on the MCAT with like hearing questions, maybe some psych-soc questions where they'll give you some examples, and then you'll understand like, oh, you'll have to understand physics, but you'll also have to understand some of the either like the biology or the biochemistry, and that's kind of how they'll ask about sound. So again, sound is created by mechanical disturbances in a material. So you can imagine like when I'm creating friction, you can hear some sounds, and that causes oscillation of molecules in the material. Propagation is what I was showing you an example of. And again, sound propagates through all forms of matter, but not through a vacuum. And you should understand why it's not through a vacuum. The reason for that is because sound needs all these particles to be moving. And so if there's no particles in a vacuum, then it's not going to move. The next thing is that sound is fastest through solids, then liquids. And then again, remember about this equation. Within a medium, as density increases, speed of sound decreases. The next thing is pitch. And pitch is our perception of frequency. So if I have a really high pitch, like my pitch is really high, like I'm an opera singer, then that's kind of how you interpret frequency of the sounds that I'm making. Okay, the next thing is Doppler effect. Doppler effect is actually kind of high yield. You'll probably get at least one question about Doppler effect on your exam. And the way that they sometimes test it is that they ask it in terms of radiology, or they'll give you like a train and they'll ask you like, how can you interpret this? And Doppler is kind of when something is moving, how do you interpret the frequency of that moving object? And so let me see if I can find an example. So this is kind of an explanation of Doppler effect, and you can see that this is one observer and this is another observer, and this is the source of the sound, the ambulance. And so this ambulance, it's going to sound like this guy is going to experience a higher frequency of these sounds because the sounds are moving towards that person. So because this ambulance is moving towards this person, these sound waves are coming at this person. And so it's going to this person is going to experience higher frequency. Whereas because these sounds are moving this way, these sounds are going to be further separated for this guy. And so this guy will experience lower frequency. So even though the ambulance is just creating one sound, the fact that this ambulance is moving, but these two people are not moving, and they're at different positions, results in the Doppler effect. And that's what the Doppler effect is. So how do we apply that here? All you have to know is this formula, which explains what the Doppler effect is. And you just need to know what is the perceived frequency, what is the actual frequency. And if we have the actual frequency, like if I told you the frequency of the sounds coming from the ambulance, then you could tell me what the perceived frequency is for either person. And all you would need to know is Vd and Vs. So remember, V is the speed of the wave speed. But then you need to tell me like what is the wave speed of the person who's hearing that wave, and that's kind of how you figure out Doppler. So this is a good explanation of it. So you can see that F0 is the observer's frequency of sound, Fs is the actual frequency of the sound, and then we have V. V is the speed of the sound waves, and then you have V0, which is the observer, so the velocity at which the observer is experiencing the sound, and then we have Vs, and Vs is the source velocity. So this is speed of sound, this is source velocity, so the sound of the ambulance driving. This is the observer velocity, so what is the velocity at which the observer is experiencing those sound waves? This is the frequency at which the ambulance is making those sounds. And then if you have all that information, you can figure out what is the observer frequency of that sound. So this is a good place to understand Doppler effect, and this is basically saying what is the observer frequency of the sound based on the actual frequency of those sound waves. So how we do this is we just take the speed of sound, right, the speed of the sound waves, and then we add to it the observer velocity. So if the observer is not moving, then this is 0. And then in the bottom we add to it the speed of the source velocity, right? And in this case, this would be the speed of the ambulance. So we do that calculation, we multiply it by the frequency at which the sound is coming, and then we get the observer frequency of sound, and that's what the Doppler effect is. Now it's important to mention that this is plus minus on the top and bottom, and the plus minus is coming from, so if the sound is going towards the person, then you use the plus at the top and you use the minus at the bottom. And then if the sound is going away from them, then you use the minus at the top and then the plus at the bottom. That's just something to know. Okay, I'd recommend doing like a practice example with this, and then you'll have it down because it's kind of hard to just understand it by somebody explaining it. Okay, then the next thing is intensity. So intensity is just related to an amplitude. So if it decreases over distance and some energy is lost due to attenuation from frictional forces, but it's just really important to know this equation. Intensity is equal to power over area. So the more power you have over the smaller area, that's how intensity increases. Okay, this is where we get more into the things that I told you I'll get into, which is resonance and damping. So there's strings and open pipes. And we can have closed pipes and open pipes. So let's first talk about open pipes. Open pipes are represented by L equals this N times a wavelength divided by 2. And N is just any whole number, 1, 2, 3. Then we have closed pipes. Closed pipes are represented by this equation, L equals N times wavelength divided by 4. And you'll always have odd multiples of quarter wavelengths. So it'll be like 1/4 of the wavelength, 3/4 of the wavelength, whereas these open pipes will be 1/2 of the wavelength, 1 of the wavelength, 3/2 of the wavelength, things like that. And so this is basically describing the length of the pipe that'll allow for either an open pipe or a closed pipe. And when I talk about open pipes, you'll see that closed pipes are closed at one end, so it'll be kind of like open pipes will be kind of like this, or this, or this, right? Versus closed pipes will kind of be like that, or that, or that, right? It won't be the full wavelength. It'll be a quarter wavelength or a 3/4 wavelength. And so that's kind of how you can think about open and closed pipes. Okay, next I'd like to tell you about next let's talk really quickly about ultrasound. So ultrasound are really cool devices. They use high frequency sound waves, and basically they send these sound waves, and then they are able to see when do those sound waves come back, and based on that they can figure out density of tissues, and they can figure out flow of blood within the body. It's like science fiction things, very cool. And sometimes they'll use Doppler effect with ultrasound to kind of test whether you know Doppler effect. These are harmonics, so as a shortcut, if you see that the string is attached on both ends, then you can kind of just use the number of antinodes, and that'll tell you which harmonic you're looking at. So this is the first harmonic, this is the second harmonic, this is the third harmonic. And this is kind of the wavelength that I was telling you about. So again, you can use this open closed pipe concept and figure out what is the wavelength. So this is the wavelength is 2L. This is L over here, and the reason why the wavelength is 2L is because this is just half a wavelength. So if you were to make the full wavelength, it would go like that, and that would be 2L. This is just one wavelength, right? From one point to the same point on the next wavelength. And then this is actually, that's one wavelength, and then this is another third of a wavelength. Sorry, that's another half of a wavelength. So that's 3 halves of a wavelength. And so that's why the wavelength is equal to 2/3 if you take the reciprocal of L. I told you that I would tell you about resonance and damping. So the resonance is kind of when you increase the amplitude by adding a natural or resonant frequency. So something that increases amplitude. And damping is the opposite. It decreases the amplitude because you're applying this damping force. So it's kind of in the name there. Okay, the next concept is electromagnetic waves. Electromagnetic waves are what I was telling you about light. These are transverse waves that consist of oscillating electric field and oscillating magnetic field. So it kind of has this, I'm going to show you an example. So this is electromagnetic waves. You can see that this is an oscillating electric field over here, and then this is an oscillating magnetic field over here. And so they're perpendicular to each other, and that's why this is an electromagnetic field. Okay, so the two fields are perpendicular to each other in direction of propagation of the wave. Then we have the electromagnetic spectrum, and those are the range of frequencies and wavelengths found in the EM waves. So this is the electromagnetic spectrum over here. And you can see that it goes from gamma rays, which are really, really high frequency, all the way to radio waves, which are very low frequency, high wavelength. And in the middle, there's visible, which is actually a very small portion of this electromagnetic spectrum. And that visible is just the things that we can see. So I would know that 400 is violet and 700 is red, and these are the wavelengths in nanometers. Okay, the next concept is hydrogen spectral series. So if you remember in the chemistry lesson, there was kind of this whole belief that, you know, that there's this hydrogen atom, and then around it there's these electrons, and then based on where the electron comes back to, so let's say that we go from here, let me show you an example. Okay, this is a good example. And basically when an electron goes from a higher orbital to a lower orbital, or sorry, I should say orbit. When an electron goes from a higher orbit to a lower orbit, it's basically releasing energy. And so that energy comes off as light. And that's light sometimes that we can see. And so for a hydrogen atom, they did these experiments, and they found that when an electron goes to the first orbit from any of the outside ones, it looks violet, and that's called the Lyman series. And you don't need to know these names, you just should probably know the color. And then you should also be able to tell me why is that color the color that comes out. And so anything going to the first orbit, that's actually releasing a lot of energy. And if you remember, the really high frequency color is violet. Now going to the second is called Balmer, and that's going to be like this bluish color. Then you have passion, and then you have bracket, and that's to the third n equals 3, and that's to the n equals 4. So this is n equals 1, this is n equals 2 over here, n equals 3, so this is 4, and then this is 5. And then if we go back, we can kind of see what the colors are. So Lyman is ultraviolet, Balmer is visible, passion is infrared, and then this is kind of an acoustic love's beer pong, n equals 1, 2, and 3. And so the idea here is that when these electrons are going back to those shells or those orbits, that's the color that's coming out. Okay, then we have Rydberg's formula, and that's basically what I just told you. And that's how you can figure out these colors, because you take the n final and the n initial. So if we're going to 1, it's if we're going to 1, then n final is 1. If we're starting from 2, then n initial is 2. So this would be 1 minus 1/4, and it would be 3/4 times this r value is equal to the frequency times this h value. And then we can figure out what is the frequency of light that's being emitted from the electron going from high shell to low shell. Okay, the next thing is diffraction. Diffraction is the bending and spreading of light waves as they pass through a narrow slit. And diffraction can create this large light fringe surrounded by alternating dark fringes and light fringes with the addition of a lens. So it's helpful if I show you an example. So this is diffraction over here. You can see that this person has this sight, and then this light kind of goes and bends around this slit over here. And I think a better example would be right here. And if you see that there's these waves coming in this way, but then when it hits the slit, it starts to diffract or bend, and that's what diffraction is. And the larger the slit, the less bending that happens, but the smaller the slit, the more it kind of curves that way. Okay. And you can see here wavelength is really high, is much greater than slit length here, and then wavelength is about slit length here, and then wavelength is much less than the slit width here. And that's kind of how you can imagine it. Okay, this is a good example of what I'm saying. So this is a small diffraction effect, and this is a large diffraction effect, and it's because this is a narrow gap and this is a wide gap. Okay, the next thing is interference, and this is kind of what I've already talked to you about, which is that when waves interact with each other, displacements add up, and that's called interference. Now we have Young's double slit experiment, and this is very important. So this is a good image I found on Young's double slit, and essentially you send these electrons here. This is probably better. You send these electrons into a double slit, and then what happens is that it goes through both these slits, and then those electrons interact with each other, and they create this interference pattern where it's very dark in the middle, but you can see that all these columns of where the electron is hitting is surrounded by these light areas where there's no electrons hitting. And you might ask yourself, why is that happening? And the reason is because these slits are like these electrons are interacting with each other, and so when they interact with each other, they're causing these little parts of darkness. But then there's also places where the positive of this is interacting with the negative of this, and they're interfering with each other in a way that there's no electrons hitting that area. And so that's why you get these dark spots and light spots right next to each other, and that's Young's double slit experiment. So it says, shows the constructive and deconstructive interference of waves that occurs as light passing through parallel slits resulting in minima, which is the dark fringes, and maxima, which is the bright fringes. Then we have polarization. So plain polarized light is that it's kind of like when you're wearing these polarizing glasses, and it only lets light through a filter if the electric field of the wave aligns with the openings of the filter. So remember, the electric field is kind of like in a certain direction, and so the electric fields of the exiting light oscillate on the same axis. And so this is an example of a plain polarizing light, and so you have this light and it's going through, but then this is the polarizer, and it's only allowing these vertical lines to go through. And so what you have at the end is just these vertical lines. They only oscillate against this plane. They don't oscillate in all the planes like this. The circular polarized light is kind of the same thing. It's the idea that this is constantly rotating direction. So instead of this being a stationary thing, it's constantly rotating like this. And so you kind of have this very unique pattern. And so circular polarized light is created by exposing unipolarized light to special pigments or filters. Okay, now we get to kind of like the much harder things. These are things that took a long time to kind of understand, so I'm going to go a little bit slower through this, and so making sure that we understand this. So reflection is actually pretty easy. Reflection is just that's something you know. When something goes in, it reflects off an object and goes away. And the important law of reflection is that this theta 1 is equal to theta 2. And this theta 1 is called the angle of incidence, and theta 2 is the angle of reflection. And you just draw a normal line to where the ray is hitting the mirror, and then it reflects, and that's how you find these two angles. And the important law here is that these two angles are the same. So that's what this is. Okay, next you have spherical mirrors. This is where it gets kind of harder. So I would recommend just kind of memorizing this. It's really hard to understand why it occurs, but if you understand this and then you kind of understand this, then you'll be solid. So let's start with this. When you have like this object over here, and then you have this center of curvature, and this object is further away from this center of curvature, what you end up with is this image over here, which is kind of inverted, and it looks smaller than the original object. Now, when you have this object over here, the center of curvature is actually way behind the mirror, and so what you get is this virtual image. This virtual image is much smaller than the original object. And the focal point is all the way back here. So here the focal point is behind the virtual image, and it's also important to know that the focal point is in front of the center of curvature. These are concave mirrors, so concave looks like a cave. These are convex mirrors. Convex is kind of like a V. I don't know if that helps you, but that's kind of how I think of it. So concave is like you're looking at this, and this is you, and then convex is this is you, and this is the mirror. So that's how you can think of it. Now it's also important to know that this is a concave mirror, right? But then you have to know, is the object's position over here where it is right now? And I'm talking about concave right now. Is the position over here, or is the position over here? Because depending on where you're standing compared to the mirror, it's going to change how the image looks. So this is what took me a long time to understand. But let's say that you're standing behind the focal point, right? Then we have the real and inverted, because the object's position is greater than the focal length. So just this is where we are, this is where the focal point is, and so because we are further away from the focal point, it's going to be real and inverted. Now let's say that we're actually standing closer to the mirror, right? The object's position is less than the focal length, so we're standing closer to the mirror than the focal point. What that's going to result in is it's going to be virtual and upright. So actually this mirror, our reflection, will be upright. It's no longer going to be inverted. Now this kind of makes sense if you think about it. If you're standing really close to this mirror, it's kind of going to look a little bit straighter, versus if you stand a little bit further, it's going to look a lot more curvy. And so that's kind of why when you're standing close to the mirror, you get a virtual and upright image, because it looks a little bit straighter, and so that's why you look upright, versus when you're looking at it from afar, it's so curved and then you look upside down. So that's kind of how you can understand that, and you can understand that. Now it's about convex, virtual, upright. Also, one more thing I should mention is, what is this focal point? This focal point is the place at which these light rays reflect and interact with each other. So these light rays come and then they interact at this focal point. So if you have light rays coming over here, and then they interact at this focal point. So that's kind of how you can think of focal point. Focal point is the point of focus of the rays. Okay, center of curvature is kind of like if you made this into a circle, where would the center be? Okay, now we have convex, virtual, and upright, and smaller. So fortunately for us, it's kind of easy to remember this, because there's only one thing, which is that you're standing somewhere, and no matter what, you're just going to look upright and smaller. So you're going to look like a small guy in this mirror reflection to you. The final thing, and then it's also important to know that your focal point is going to be in front of the center of curvature. Okay, the final thing is the plane, and this is just a normal mirror. And so a normal mirror is going to give you a virtual image. It's going to be upright and the same size. So if you're just looking at a mirror, it's going to be looking the same size as you, and it's going to be upright. So it's just going to look exactly like you. And this is a virtual image. Okay, and you can, a way that you can think of this, it's kind of a little bit more complicated, but they're kind of like spherical mirrors, but they have infinite radii of curvature. So what that means is that this is just like this is like a mirror, but the radius is just infinite, and so because of that, this just becomes straighter and straighter until it's just straight. And so that's a way you can think of it. I never really found that helpful, so I just think about that it's just a plain mirror is just a normal mirror. Okay, so I hope that helps with spherical mirrors. This was always really confusing to me. Okay, the next thing is refraction. Refraction is, let's say that there's a light ray and it's hitting the water. Now, this light ray is actually not going to go straight through. It's actually going to pass like a little bit, it's going to refract. It's going to bend a little bit. And that bending of light is called refraction. Now, this is caused because of speed change, and it's because light moves differently in different substances. So in air, it's going to move at a different speed than at water, and so that's what you can figure out what the index of refraction is, n, by just figuring out what is c. C is just 3 times whatever the speed of light in a vacuum divided by the speed of light in a medium, and based on that you can figure out n, which is the index of refraction. Okay, now we have dispersion. Dispersion is just when various wavelengths of light separate from each other. So let me show you an example. So this is dispersion of light. It's just when you go through a prism, or if you think about rainbows, it's caused by dispersion of light through raindrops. Okay, the next concept is Snell's law. Snell's law is the law of refraction. And remember when I was telling you about how light bends when it goes from air to water? Well, now you can actually figure out mathematically what is the angle at which it's bending. And that's a really helpful thing to know. So basically what we do is we take n1, which is the index of refraction of whatever is the first substance, and then we do n2, which is the index of refraction of the second substance, and then we take the theta of both angles, and we can now figure out, well, if we have the theta of one of the angles, then we can figure out what is the bending of the second angle. So it's important to know that this is measured from the normal. So let's say we have light that's coming in this way, and then it hits the water and then bends this way, right? So we need to know that the angle is this angle over here. And let me show you a picture. So this is a helpful picture over here. And so let's say that this is the light is going this way, right? I'm gonna let that erase. Okay, so let's say the light is going in this direction, this way, right? So first we draw a normal line. So this is an up and down line, and then we have the theta 1, which is this angle over here, and then we have theta 2, which is this angle over here. Then we should know what these two substances are. This looks like water, this looks like air. So you'll be able to calculate n2 and n1, and they should be able to tell you, like, this is the angle at which light is hitting the surface. And so based on that, you can figure out, okay, this is what theta 1 is. Now I should be able to figure out in which direction is the light going, and that's what theta 2 is. And so that's how you would answer Snell's law questions. Okay, the next question is total internal reflection, and this is just the law of reflection, but this happens when light is moving from a medium of higher index to a medium of lower index with a high incident theta. So what is a high incident theta? Well, it's when the theta is really large. So it would be like if this is the surface and light is hitting like at a very steep angle, like this way, right? In that case, there might be total internal reflection where it just pops right out. It's not even going to go through. And it only happens when you have a medium of higher index of refraction to a medium of lower index of refraction. So if n1 is really high and n2 is really low, so n1 is high, right? And theta 1 is high. In that case, you can just get complete reflection. And you might not even get any refraction at all. You might not even get the light to go through. So that's what total internal reflection is. Now we have critical angle, and this is the minimum incident angle at which total reflection occurs. And so if you just take this equation and then you plug it in, you reformat it, you'll get this equation. This is the critical angle. And so if the critical angle is, for example, 12 degrees, that says that at 12 degrees or less, at 12 degrees or greater, you're going to have total reflection. Okay. Yeah, so critical angle is the minimum incident angle. So if it's like, again, 12 degrees, it's going to be more like 80 degrees. If it's 80 degrees or anything more than that, then you're going to have total reflection. That's an example of critical angle. Okay, now we have lenses, and lenses was also confusing, just like mirrors to me. So I'll try my best to explain this. Lenses, again, we have convex, which is kind of like I think of it like a V. I don't know how you think of it. And concave, which is like a V, which is like a cave. That's how I think of it. But yeah, you just have to know concave is going in and convex is going out. Okay, lenses is things that light goes through, whereas mirrors are things that light reflects off of. So lenses refract light to form images of objects. And then we have thin symmetrical lenses, which have focal points on each side. So let's start with concave because those are easier. So this is a concave. And if we send light into this, then it's going to go outward, right? Which kind of makes sense. It's a cave, so it's going to go outward. Now we have the focal length, and the focal length is 1/2 r, right? And we have f, which is the focus, and little f is just the length, the distance from the focus to the mirror. So this is little f, and the focus is the big F. Okay, so when you are standing here, and you're looking at the concave lens, you just end up with an upright image, and it's virtual. So this is the T, and it ends up virtual and upright. And when you are at a convex lens, it's actually a little bit more complicated. You have a real image or a virtual image, and it depends on where you're standing. So the way that I think of it is that if you're standing right over here, then the image over here, if you look at it, will be virtual and upright, but the image over here will be real and inverted. And that's kind of how you can think about convex lenses. Okay, the final one is lens maker equations, and this is honestly not very high yield. So I would just memorize this equation, but I wouldn't worry too much about it. Okay. The next important concept is the photoelectric effect, and fortunately I've already talked about this. So the photoelectric effect is the ejection of an electron from the surface of a metal, and so when you put light onto a metal, so let's say this is like iron or something, essentially there's going to be electrons that are shooting off, and that's because you're injecting a ton of energy, and so these electrons are now able to leave these metals. And so if you want to figure out what is the energy of the photon of light, these light, remember that light has both particle and wave-like properties, and so you can figure out what is the energy in a photon of light, and that is this equation. It's just based on the frequency. You multiply that by a constant, and then you get the energy. And then if you want to calculate the wavelength, obviously, then you can just do c equals wavelength times frequency, and c is 3 times 10 to the 8th. That's the speed of light, and that's how you figure out what is the wavelength. Okay, the next thing is the kinetic energy, and this is just fortunately just the same formula. So this is always a formula that confuses people a little bit. What is this W doing here? What is that work? And essentially, it actually takes a minimum amount of work or a minimum amount of energy from this light going onto the metal to cause electrons to shoot off. So if this light energy right here, I'm going to use yellow here. So let's say this light energy over here is too little energy, you're not actually going to be able to eject any electrons. So there's a minimum amount of work that it takes, and that's what this W is, that allows for a single electron to leave. And so this W is that representation. So you're taking basically the kinetic energy of the electrons that are leaving this metal. You figure it out by taking that energy of light and then subtracting that work that it takes just to get to that threshold. So you can think of this work as the threshold that's necessary to eject any electrons. So that's what this threshold frequency is referring to. This work is in joules, and then this frequency is just in 1 over nanometers. That allows you to figure out, so yeah, this is basically referring to the threshold frequency that's necessary to eject any electron from material. You can multiply that threshold frequency by this h, and then you would get this work, the energy, and that's the threshold energy. And so that's what this work function is referring to. This h, remember, times the threshold frequency gives you the work. And you can remember h is Planck's constant, which is just 6.6 times 10 to the negative 34 joules per second. And if you look at the units, it kind of makes sense because you take this h, which is joules seconds, and then you multiply it by frequency, which is hertz or 1 over second, and then you get joules, which is the work unit. Okay, the next thing is Bohr's model. And this is just things that I've talked about before, the absorption and emission of light. So remember that Bohr believed that these electrons live in stable and discrete levels, And so when you go from one level to a different level, you're either releasing energy or you're absorbing energy. You absorb energy when you're going up a level, and you're releasing energy when you go down a level closer to the nucleus. The absorption is what I just mentioned, same with the emission. So emission happens when you go down a level, and because of that, you're emitting some energy. And usually that energy, or I should say that energy, is represented in photons of light. So remember when we were talking about all the different colors of light that happens, like ultraviolet or red? That's because these electrons go down in a level, and then you release this color of light. Okay, now you have absorption spectra, and then you have fluorescence. So fluorescence is just when a species absorbs high frequency light and then returns to ground state in multiple steps. So instead of it going down all at once, it just goes down in different steps. And then each step has less energy than the absorbed light and is within the visible range of the electromagnetic spectrum. So imagine that I shoot a ton of light into this atom. This electron jumps into like the 5th level, and now one by one it's going to the 4th level, then 3rd level, then the 2nd level. That's what this fluorescence is referring to. Okay, the next thing is nuclear binding energy and mass defect. The main thing to know about nuclear binding energy is that it has a lot of energy. So there's a lot of binding energy that's connecting these nucleons. Nucleons are protons and neutrons, and essentially that's just because those are within the nucleus. Now there's 4 fundamental forces of nature. There's what we talked about, gravity, there's electrostatic forces, and then there's strong and weak nuclear forces. And those just refer to these nuclear binding energy, the forces between protons and neutrons. Okay, now there's mass defect, and this is just the difference between the mass of the unbonded nucleons and the mass of the bonded nucleons within the nucleus. The unbonded actually have more energy and therefore more mass than the bonded constituents. It's kind of interesting why there's this difference in mass when like a proton and a neutron are right next to each other versus when the proton and neutron are separated. And so actually when these things are separated, they have more mass and more energy. Slightly more mass, a lot more energy. And because of that, the mass defect is the amount of mass that's converted to energy during nuclear fusion. Nuclear fusion, you should also know what the difference between nuclear fusion and fission is, which is what we'll get into next. Okay, so I just mentioned fusion and fission. So fusion is when small nuclei combine into large nuclei, and then fission happens when large nuclei split into smaller nuclei. So this is fission, and then this is fusion. Okay. The next thing is energy is released in both fusion and fission, because the nuclei formed in both processes are more stable than the starting nuclei. So the reason why fusion and fission happens is because the end product is more stable. So maybe in the fission process, this large nuclei is very unstable. And in the fusion process, these small nuclei really want to combine into this larger nuclei. Okay, the next thing is radioactive decay. This is pretty high yield as well. And there's 3 types of particles that you can lose from the nucleus, or I should say 4 types of particles that you can lose from the nucleus. One is this beta, which is essentially just an electron. Another one is this, which is just essentially like a positively charged with no mass particle. So one is just, you're losing something that has no mass but has a negative charge. Another one is you're going to lose something that has no mass but has a positive charge. Another thing is that you're just losing energy. So you're not actually losing mass and you're not losing charge. It's just gamma. And then the last thing is kind of like losing something that has 4 mass and 2 plus charge, kind of like a helium particle, but it has 2 plus charge. Okay, so alpha particle is, again, that's what they're comparing it to, like a helium particle, which is basically a helium nucleus. So if it was a helium atom without the electrons, that's what an alpha particle is. And so that's when you can see in alpha decay, basically you go from one atom to another atom, and the atom is losing 4 in its mass and then 2 in its charge, and you get an alpha particle. The beta negative decay is kind of like a neutron converting into a proton, because you're losing a charge, right? And so when you're losing a charge but you're not losing mass, it's kind of like a neutron is converting into a proton. That's kind of a way you can think of it. So that's what this is showing. Then you have beta positive decay, and that's kind of like if a proton became a neutron. It's like the opposite of this, because protons and neutrons have the same mass but different charges. And that's what this is showing. And then finally we have gamma, and gamma decay is just you're losing a lot of energy, which is represented in photons. And so you get like a lot of light that's leaving, and that has very high energy. So this is basically you're just going from a very high energy nucleus to a lower, more stable energy nucleus. Okay, now we have electron capture. And electron capture is just imagine that there's these electrons that are in the orbit, and now the nucleus is just going to absorb or capture this electron. And so that's what this is showing, is that we take an electron from the inner shell, and then we end up with this. So we end up with the nucleus now having one negative charge. So the charge is decreasing by 1. Now half-life is pretty high yield. You'll probably get 1 question or 2 about half-life, and it's the amount of time that's required for half of the sample to decay. So if I have 100 of, I don't know, radon, and then it becomes 50 in like 1 week, then the half-life is 1 week. If it becomes 25 in 2 weeks, you should know that the half-life is 1 week, because there's two times that it halved, once from 100 to 50 and then once from 50 to 25. So if it took 2 weeks, that means that 1 week is the half-life. This is the equation for exponential decay over here, and it's pretty important that you know this. So it's just the number of undecayed nuclei, and then this is the number of undecayed nuclei at time t equals 0. And then we have a known decay constant, and this is just dependent on what like radioactive material we're working with. And you'll actually see this in, like I was doing a rotation with radiation oncology, and some of the medicines they used, they had radioactive half-lives. And so for the doctors to prescribe these medicines to the patient, they kind of had to know, like, what is the time of delivery of this medicine and how much do we have to prescribe to make sure that this patient will be able to take enough of this medicine. So that's kind of like a clinical correlate that you might see when you're taking your MCAT. Okay. Next is this is just the image that represents everything I was talking about, and these might be able to help you understand what's going on, but I think you probably get the gist of it. Okay, I'm going to go really quickly through the math because I think that you probably know almost all of this already. So let's just go through it just to make sure you know it. So you'll know what scientific notation is. It's like when you use this 1 digit and then you multiply it by 10 to the power of something, and that can kind of help you add, multiply, subtract, divide, things like that. There's this Lars mnemonic. I've never really found it that helpful, but some people like to use that Lars left add, right subtract when they're doing this. And then there's significant figures. So significant figures is when you include all non-zero digits and any trailing zeros in a number with decimal points. Okay. In the MCAT, it's important that when you're doing math, you should just kind of be good at estimating. You don't really need to be able to do complete math with all the digits and numbers and all those things. So just get good at estimating things, because that'll speed up time significantly. Now, trigonometry is not really that high yield, but it is kind of helpful to know, like sine, cosine, theta, sine, cosine, and tan. So sine is just the opposite over the hypotenuse. Cosine is the adjacent over hypotenuse. Tangent is the opposite over the adjacent. So just make sure you know these. And then if you know this, then that's great. If you don't know it, I wouldn't spend time memorizing it. It's not too high yield. I would just know that at 0, what are these? And then I'd know probably at like 90 degrees, what are these? And that's going to be probably the 2 most high yield values that you would need to know. Okay. Next we have logs. So you're not going to need to know logs too much. They might ask you to take logs for half-lives or different types of exponential decay type questions. So I would just know logs based on that. I would try to kind of get good at, like, okay, if log base 10 of 100 is 2, then can I estimate what log base 10 of like 356 would be? Like, is it closer to 2 or closer to 3, or what would it be like? Like, that is kind of the extent of which log you might need to know. And then I would kind of know like how to manipulate logs a little bit, but again, it's not that high yield. Okay, kind of be able to estimate like, oh, is the square root of 8, like what would that kind of be close to, things like that. But again, it's not too important. I think most of the math that you'll need to know for the MCAT, you'll kind of get through practice questions, and you'll kind of get the idea. Like, you definitely don't need to understand this whole unit circle, especially if you don't recall it from like algebra 2 trig or calculus or whatever. Like, it's not super important that you remember 135 degrees is this value. It can help you, but I wouldn't waste too much time on these things. Okay, again, we'll go quickly through this. So the scientific method you've learned ad nauseum several times. You know that you have to formulate a hypothesis, test that hypothesis, and then provide results for further testing. Ethics, so you should know that medical ethics, there's 4 like huge tenets of medical ethics. You're going to be it's going to be helpful in like interviews and when you start like clinical rotations in med school to know these 4 tenets, which is beneficence, do good to your patients; non-maleficence, don't do any harm to your patients; respect your patients' autonomy, so like respect their decisions when they're capable of making those decisions; and then justice was always the hardest one for me. But justice is basically, you have limited resources as a clinician, so how are you going to decide how to distribute the resources that you have for the patients that you have. Research ethics essentially is pretty similar. You just have to have respect for people, resources, making sure that you do good by people. And then this is kind of an important point, which I learned about a lot more recently in college, which is that when you're doing a lot of these clinical trials, your ethical responsibility is that if you're doing like if you're giving like 2 different types of treatment, like treatment A and treatment B for a population, like let's say that you're treating cancer patients and you want to figure out like, is this medicine good or bad? And you're giving that medicine and then you give like the standard treatment and you kind of compare the 2 samples. The moment that you realize that, you know, one treatment is better than the other, you're ethically obligated to kind of like stop the experiment, or to make sure that the patients, especially if it's going to extend their life or stop them from dying, you're not allowed to continue giving them an inferior treatment just because you want to like complete the study, because that's kind of against ethics. And you can read more about that. I'm kind of summarizing it and not doing the justice to it, but that's kind of the main idea of research ethics. Okay, research in the real world, so you should know populations, all the individuals. Samples is just a subset, and sample data is called statistics. You have internal and external validity. So internal validity is this experiment like correctly done? Like, is the dependent variable the result of manipulating the independent variable, or are there confounding variables that the researchers haven't accounted for? External validity is like, can this actually be generalized to the main population? So if I do a study on smokers, but then I say like, oh, exercise is good for everybody, but I only did this study on smokers, and that kind of has that statement has low external validity because I've only done the study on a specific subset of the population. Within subject design, it's important to know that, so controls for individual variation. And then we have statistical significance. So what is the chance that this result is due to chance? There's always a small percentage likelihood that like the differences in the clinical outcomes is just because of chance, and so we want a high statistical significance, so that we know like, oh, this is probably because of the differences in the independent variable, not because of chance. Clinical significance, so like how important is it for patient outcomes? It's important to know like moderator variable, mediator variable, dependent variable, and hopefully we just get independent variable that affects the dependent variable. Okay, we have basic science. So you have variables, independent, dependent variable. We have positive controls, negative controls. Positive controls ensures that the change in dependent variable occurs when it's expected, and negative controls occurs when there's no change in the dependent variable, when none is expected. I'll try to think of an example and then show you. Okay, this is a good example of positive versus negative control. So let's say my experiment is I give some people orange juice and I give other people no orange juice, and then I see like what is the difference in their let's say I give some people water and some people no orange juice and some people orange juice, and my outcome is I want to measure their vitamin C levels at the end of this, or I want to see like which patient population has more scurvy. So you might say like, okay, well, orange juice population is going to have more vitamin C at the end of it. But then what if it's because of something else in the orange juice, or something that we're not accounting for? Or like, what if the people who are having orange juice are just in general, like, I don't know, going out in the sun or having more leafy vegetables or something, and that's resulting in the thing. So then you have positive controls and negative controls. So positive controls, you give some of the patients vitamin C and you see like, oh, is that actually resulting in what I want it to result in? And then you give some a negative control, which is like I give them water and then I see like, is that resulting in what I'm expecting to? And so as long as the positive control results in what you're expecting and negative control results in what you're not expecting, you're increasing the internal validity of your study. Okay, now we have accuracy and precision. I'll show you an image of this. So this is accuracy versus precision. This is also kind of high yield. This is high accuracy, low precision. This is low accuracy, high precision. So accuracy is how close do you get to the target. Precision is how close to the dots the different trials get to each other. Okay. Next we have human subject research. So you have cohort studies, you have cross-sectional studies, and then you have case control studies. So make sure you understand the difference between these. Cohort studies is you look at it throughout time, you look at a cohort throughout time, and then you assess the rate of a certain outcome. So let's say I look at a ton of smokers over time and I see like how many of them do get like lung cancer or different types of cancer. Cross-sectional studies is I look at a single point of time and then I'm figuring out like how many of these people have been smokers and then how many of them have cancer at the moment. And then you have case control studies. So you look at some people who are in one group, and then you look at the outcome first. So you look at, okay, how many of these people have lung cancer at this moment of time? And then based on all the people who have lung cancer, then you go back and then you look at their charts and look at how many of these people have exposure to smoking. And that's kind of like a case control study. Hill's criteria figures out if causality can be supported. This is not too high yield. I wouldn't spend too much time on this, but biases is pretty important. I would understand biases. So you have selection bias, detection bias, Hawthorne effect, social desirability bias. So I'll start with Hawthorne effect. That's just if you're being observed, you probably will change your behavior. If somebody was watching me how many times I'm exercising in the week, I'm going to exercise more just because I know I'm being watched. Selection bias is like the idea that I'm choosing people who are different from the population. In clinical trials, you have a lot of selection bias a lot of times because a lot of the people who are doing something are usually like volunteers for those experiments or people who are getting paid some money. And so that chooses maybe some specific people that are different from the population. Detection bias is from the educational professionals that are using their knowledge in a way that's inconsistent and by searching for an outcome disproportionately. So if I gave like pathologists a lot of slides and I told them like figure out like how many of these people have lung cancer or something, and I told them like, oh, all these people are smokers, and this file all these people are not smokers, like maybe there's some detection bias over there. And then there's social desirability bias. So if I ask like everybody who has lung cancer like how many times have you smoked in the past, there's some social desirability to say like, oh, I haven't really smoked in my life, things like that. Placebo effect is the idea that results are influenced by the fact that subjects are aware whether or not they're in the control group. So you want to make sure that they're blinded to it. So make sure that they don't know whether like the pill is a placebo or whether the pill is whether they know like the pill is like supposed to have some effect or whether they're just not receiving a pill. So just give them like a placebo pill and don't tell them like, oh, is this tell them like this might be a placebo pill or this might be the pill that we're hoping will have an effect. Confounding variable, that's an extraneous variable that affects both the dependent and independent variable. You have mediating variable, which is over here, which is like a middleman between the independent and dependent variable. And then you have moderating variable, which influences the relationship between the independent and dependent variable. Okay, now we have measures of central tendency. So we have mean, median, and mode. This is really important. It just means that you need to know mean is the average, median is the middle of the data set, mode is the most often data point. Normal distribution, the median and the mean are the same, so is the mode. You should know these standard deviations and the percentage of the population that exists within these standard deviations. So 68% in the first standard deviation, 95 in the second, and 99.7 in the third. There's also standard deviation. In a normal distribution, the mean is 0, the standard deviation is 1. In a skewed distribution, you can have left skewed or right skewed. This is they like to test this sometimes, so they can test median and mean. So just know like left skewed, there's like a long tail on the left, and right skewed there's a long tail on the right. And so left skewed, the median's on this, sorry, the mean is on the left and the left skewed, and the mean is on the right and right skewed. Now there's bimodal distribution. That means that there's multiple peaks. And so you can get like, yeah, you can have multiple peaks in a bimodal distribution. There's measures of distribution. So range is the difference between largest and smallest. There's interquartile range, which is the third quartile and the first quartile. So 25th percentile and 75th percentile. Standard deviation is the measure of variability around the mean. And then outliers is anything that's more than 3 standard deviations away from the mean. So that can be above or below. Yeah, these are the relationships. So this one over here, this is exponential, then there's logarithmic, then there's quadratic, and this is curvilinear. It's just quadratic upside down. You have probability. Independent events is like flipping a coin twice. It doesn't affect the probability the second time. Dependent events, it does affect the outcome of the other events. Terminology is mutually exclusive, means that you cannot occur simultaneously. And when a set of outcomes is exhaustive, then there's no other possible outcomes. So mutually exclusive, like getting a heads and tails when you're flipping a coin, that's mutually exclusive. And then when there's a set of outcomes that's exhaustive, then there's no other possible outcome. So when I flip a coin twice, I can get 2 heads, 2 tails, 1 head, 1 tail, or 1 tail, 1 head. That's an exhaustive set of outcomes. Statistical testing, so there's hypothesis test. We want to figure out whether the null hypothesis can be rejected. P-value is how we do that. There's a significance value. Usually significance value is 0.05, which is that we're allowing 5% probability that the outcome can happen by chance. And then p-value is what's the probability that this outcome happened by chance. So the p-value is like 0.001. That means that there's a really small likelihood that the outcome happened by chance. So it means that we can probably reject the null hypothesis. Confidence intervals just tells us about the range of values around a sample mean. So usually we use a 95% confidence interval. It's important to know type 1 and type 2 errors. Type 1 error exists over here, and type 2 errors exist over here. So type 1 errors is, let's see, in this example, they say passenger is safe, passenger is potentially dangerous, passenger is innocent, passenger is not innocent. So in a type 1 error, you say it's a false hit. You assume that they're dangerous, but they're innocent. And then type 2 error is a false miss. Let me find a better example for you. Okay, this is a good example over here. You can see that there's a minor's decision of an actual emergency. So if there's an actual emergency, then you get a yes, a hit. And if there's no emergency and the minor decides no, then it's a correct rejection. But a type 1 error is that the minor decides to panic even though there's no emergency. A type 2 error is the minor decides not to panic even though there is an emergency. So that's like a false alarm versus a miss. So we call this type 1 error false alarm, and we call this type 2 error a miss. Otherwise it's a hit or a correct rejection. Okay. Finally, we have charts, graphs, tables, and this is just pie or bar charts, which is for categorical data, histograms and box plots as numerical data, and then linear, semi-log, or log plots you can use by distinguishing the axis. And usually this is just used for convenience to kind of, the log plots to kind of show the data in a more presentable manner. Slope is obviously the rise over the run, so the change in the y over the change in the x. And that's all of the physics and math that you need to know for the MCAT. I hope this was helpful. Thanks so much for watching, and I'll see you in the next video. Bye, everybody.